morning, everyone. Welcome to this day of the Spm Smi Office. My name is Chalma, the General Chair of the conference. And it's my great pleasure to host the second keynote of the conference. Give it to a talk from Professor Bernardo. I know Bernardo for many years, but we have collaborated the last with person is around 10 years ago. Okay, this is some of the gems like during the a lot of things like this. It's like pandemic, it's like many of the chances of in person stuff like that. And Bird has a fantastic. And he's a currently a professor of computational design at ETH, and he's also a research scientist at Google. And he previously served as professor and vice president at like an ISTA at 2020, it's like Institute of Technology, right? Okay. And worked as a research scientist at Disney Research. And he received his PhD in computer science from ETH, which is kind of 10. His research interests kind of intersect multiple areas, including visual computing, digital fabrication, machine learning, and focusing on computational tools that bridge the digital design and physical manufacturing, as like we know each other very well. Okay. And his work includes the high fidelity of performance picture and data-driven material modeling, functional materials, creative AI, and generative design, integrating physics-based solutions, machine learning to create high-performance structures and systems. And Merck's contribution have been recognized with the technical achievement award from the Academy of Motion Capture Arts and Science, and ACMC grants significant new research 2017, and the ECR are starting around 2016, and the ECH medal is like 2011 is doctor dissertation. Okay, thanks and welcome, Bern, to come to the stage and give us that.
Yeah, thank you so much. Thank you so much for the kind introduction. Yeah, it's a true privilege to be here. Really amazing and beautiful. Okay, perfect. All right. So yes, thanks again for the very kind introduction. Also, big thanks to all the organizers. Fantastic to be here, and yeah, it's a really beautiful city. So in my talk, I want to explore the transformation of design workflows from traditional CAD towards intelligent design systems. And I think in general, computational design is a very exciting topic because basically design is everywhere. It is in everything that we need to create. It's in buildings, in the built environment, in everything that engineering creates, in material structures, and even in computer science in the form of data structures, neural network architectures, and programming languages. And now I think it's fair to say that in all of these areas, actually finding excellent designs is extremely challenging because we're facing very complex problems that go actually also beyond pure performance. So they also include factors such as, for example, environmental sustainability, cost effectiveness, and also communication challenges between stakeholders that need to work together to actually, solve a complex problem, just to name a few. So I think across all these application areas, there is one very central challenge, and that is how can we more efficiently do design? How can actually machines create complex designs? And how can machines actually work together with humans to create designs? And what are the key problems actually such that machines and humans are actually successful in finding good designs? Now, I think this topic is extremely timely. So we are all witnessing this omnipresent rise of technology across all fields. And in particular, we see this exponential acceleration of AI. which comes with really disruptive possibilities for analyzing vast amount of data, and also the generative capabilities when it comes to images, text, or code, are truly stunning. On the other hand, in particular, when it comes to solving difficult, for example, difficult to define problems, the human has very unique skills when it comes to uh, creativity, empathizing with each other, also framing the problem, and also ethical decision making. And then on top of that, that's also my role actually at Google. I'm in the XR team. So there are also new spatial compute platforms on the verge, for example, augmented reality. So there you can, for example, imagine a device that can actually sense the environment, basically see what you see, hear what you hear, and also have a display that allows you to seamlessly blend between virtual and the real world. And this together, I think, really provides exciting possibilities of bridging humans, AI, and their surrounding, and thereby unlocking new workflows. Now, a large part of our research is actually motivated by the belief that there is actually an urgent need to harness the potential of this technology while also preserving the human creative process and basically ultimately empower humans, so basically giving humans superpowers to do design. Now, to get there, we're facing many interesting technical challenges, and one very central challenge, in my opinion, is this question and challenge around control. So what I mean by control is actually that an engineer, an artist, or designer can very accurately specify what they want to model. And this challenge is, of course, also tightly coupled to computer graphics, to our community, which is very much centered around 3D modeling and tools to actually create content. And if you think about the last 50 years of research, the history of computer graphics basically is first came control and then quality. So it actually took decades to establish the right abstractions, curves, triangles, polygons, meshes that would allow us to draw exactly what we want on screen. And while they got complemented recently by some volumetric representations such as 3D Gaussians, in general, these fundamental building blocks haven't changed much over the last decade because I think they proved to be the right ones. But what's dramatically different is the visual quality. So here we actually saw big changes going, for example, towards real-time photorealistic rendering. So to summarize, in classical CG, basically we first define exactly what we want to draw, and then it gets drawn. Now, if you look at today's AI capabilities, this actually have completely inverted this progression. So today's generative models is actually achieve photorealistic rendering quality, basically in some sense replacing that entire traditional graphic stack through massive scale training. So with a simple prompt, one can generate really stunning photorealistic images. So what you see here is actually a result for a design study for a facade, actually from an architecture student from a course that I'm teaching at ETH. And yeah, so basically generative AI models, they aim to learn this underlying probability distribution of data they're trained on, and allowing you to actually generate new samples that actually resemble the structure in that trained data. And comparing it with classical graphics, basically the deterministic nature of the graphics pipeline has been replaced by probabilistic models. Now, on the one hand, this is really amazing because now everybody of us can, in just a few seconds, generate photorealistic content, something that is very, very difficult to do with a traditional approach. But as the downside, actually, we lack precise control that actually decades of CG research have provided. So we cannot easily adjust the geometry or materials or manipulate light with the granularity that, for example, a good designer would expect. So in terms of granularity of control, there's a really huge gap between what traditional graphics technique and Gen AI can do. And one very obvious, but also I think very relevant question is, in my opinion, how can we actually close this gap? So how can we work towards systems that can provide us basically the best of both worlds? On the one hand, intuitive high-level prompts, for example, as provided by text-to-image AI models, but also benefiting from precise control of traditional graphics representations. my group tries to tackle this and also other challenges by basically trying to find solutions that are grounded in geometry processing, physics-based simulation, and then also somehow combining it with insights from machine learning and programming languages. And just to give you a very brief overview of what we did. So in the past, we focused actually quite a bit on human modeling and perception, and more recently now started shifting our focus to XR and scene perception, as well as also using or utilizing large language models for design. And yeah, a major focus is computational design tools with very broad range of applications. So for example, we've been working on material representations, designing architected materials, speeding up simulation and optimization approaches to enable interactive design. And we also try to gain a deeper theoretical understanding in design spaces. Yeah, finally, we're also very much interested in actually applying design for construction and manufacturing purposes. For example, designing molds for injection molding and casting, or designing new closed loop controllers for material deposition strategies, for example, for 3D printing. Yeah, now actually, as promised, as part of this talk, I want to explore this transformation of design workflows from traditional CAD tools towards learning-based design systems, and try to illustrate this with multiple examples. And my intention is actually to focus a bit on the navigation aspect, so basically categorizing how designers move through design spaces. So we'll actually start by presenting a general simulation-based approach for optimizing CAD data, where we basically move along gradients of explicit constraints. And then we will look at some more interactive approaches, which will allow to keep the designer in the loop and yeah, interactively allow the exploration and also optimization of designs based on, for example, some trade-offs. And there, surrogate models actually allow to predict, for example, complex material behavior, such as bending behavior, for example, of wood or glass in real time. And then towards the end, we will look a bit towards AI and more data-driven approaches, actually navigating some learned latent spaces, touching both briefly on diffusion and vision language models. And yeah, and then I conclude by trying to speculate a little bit about the future. All right, so with this, let's get started with this simulation-based approach. And yeah, basically, I think an important aspect or important practical step so that humans and machines can actually efficiently do co-design is actually to have optimization methods that can work on parametric surfaces. So basically, and this is the community here, basically all popular CAD tools, they work with parametric surfaces. They are the representation of choice for many engineering applications, also construction, robotics, architecture. And yeah, this idea of using such mathematical parametric surfaces is quite old, right? It goes back to the 50s and 60s, but it's still the method of choice in CAD, as it allows to mathematically very precisely define surfaces with, for example, smoothness guarantees, for example, perfectly rounded off edges or holes with very easy and intuitive to control parameters. Now, this is great, but now if someone wants to actually test the design and simulation, the typical workflow is usually that you start with a parametric CAD model, as you see on the left, but then you somehow have to mesh it. Then you run a simulation on the mesh domain, for example, run a finite element simulation to test occurring stresses, just to give you an example. And then for optimizing the model, of course, the CAD model needs to be updated based on the analysis. So we actually we want to know now, how does our analysis, the basically performance of the part, change with respect to small changes of the parameters of the model. And for this, ideally, we want this process to be smoothly differentiable. And one challenge is that at least if you do it naively, this is not the case here. So the problem is basically with each update, for example, by enlarging the hole in this example, we need to create a new simulation mesh. And as you know, I mean, meshing itself is non-trivial. And even if it's successful, the problem is that the mesh combinatorics change. So this can actually create some noise in the simulation which can, for example, yeah, have challenges then with having this being smoothly differentiable. So, in our work, in one of the papers, we try to address this problem by actually creating a pipeline that allows to easily optimize CAD models automatically. So the idea is that we start with the CAD model as input, then parameterize it. So basically telling the simulation which high-level parameters can be changed. And then at the core of the system, which is also the main contribution of the work, is basically analysis based on XFEM, which is fully differentiable and allows fully automatic optimization of models based on some desired objectives. And as output, we get actually an optimized CAD model, which can then be further used, for example, in an existing CAD workflow. Now, as I mentioned, the approach is based on the XFEM method. So this is an extension of the classical finite element method with the advantage that the boundary of the object we want to simulate doesn't need to exactly match with the underlying simulation mesh. So for example, we can use a regular simulation grid and embed the object in there. So for example, when looking in one of these elements, parts of the objects can be inside and parts outside, which is fine. So there is no headache about meshing that needs to conform to boundaries. Now, fortunately, as always in life, there is no free lunch. So even we have that, we still actually need to be able to accurately integrate certain quantities over the object's volume to run the simulation. And this, in the first step, might look like a challenging problem. For example, when looking at this cooling unit, because we require a method to integrate over all the subvolumes and over the regions of the model surface. And I mean, typically in numerical analysis, one would use a quadrature rule, which means basically approximating this a definite integral of a function with a weighted sum of function values at specified points, where the weights would be pre-computed. But in our setting, we cannot pre-compute the weights because we want to update the model. So the model itself is actually changing all the time. However, the good news is, that there is actually, in the paper, actually, I will not go into details, but we discovered a method for doing this precisely, efficiently, robustly, which actually, as a result, allows us to achieve a good precision and then basically be able to use the XFM method in a differentiable way and running optimization on CAD data. So yeah, as I said, because of time reasons, I will not go into details. But if you're interested in check out the paper, or we can talk during the break about it. Now, now trust me, assuming now we can run the simulation in a robust way, an efficient way. What I want to focus a bit more is actually now for performing the optimization. It's actually important to be able to specify what should be optimized. And yeah, this is a bit what I want to focus on here. So a good parameterization should provide sufficient degrees of freedom to enable meaningful improvements of combinations of objectives while actually preserving the underlying design intent of the CAD model. And on a low level, we present the CAD model, for example, as NURBS patches, and their control points are denoted here as Q. And it would actually be a bad idea to directly start manipulating these nodes, because if you start moving them around, right, you basically lose the design intent of the model. So what we rather want to do is we want to allow the user to describe some intuitive high-level parameters, such as, for example, the radius or center of a hole. And then, of course, these high-level parameters, here denoted as P. From those, you can then compute the control points Q. And by only modifying these low-level parameters indirectly through P, primitives actually retain their shape. However, in addition to that, you also need additional constraints to preserve the design intent of the CAD model. And just to give you one example, is this fillet here, which you can see in the middle, which is an initially sharp edge that has been rounded off by adding a cylinder segment. And this cylinder is actually tangent to the planes of this cube. And if this tangency is not preserved, then actually, sharp edges could occur, and you actually start breaking the model. So to solve this, actually, once a CAD model is loaded, what we do is we actually traverse all pairs of adjacent surfaces and detect tangency relationships that need to be preserved. And this is done automatically by basically using a lookup table that stores possible relationships between primitive types. And whenever a situation like this is encountered, actually a list of implicit constraints is generated for the pair of surfaces in question. And then, yeah, this yields nonlinear constraints that basically need to be retained during the optimization. And yeah, also on top of this, we have a UI which actually allows the user to define some high-level uh, uh, model parameters, for example, to keeping certain surfaces fixed or to enforce, for example, symmetries in the model. And now with this, and yeah, that we actually have this robust underlying XFM method, we can actually now run quite nice optimizations. And I want to show you some results. For example, starting with this simple wrench. So this model here is composed of a set of NURBS patches that are subject to many tangency relationships along its each edges, which you see on the right-hand side. And the parameters here are the slot, the hole, and the fillet radii. And you can now see how it's first modeled in the CAD tool, then optimized with our framework. And then after that, you can actually see you can even go back to the CAD tool and keep changing things. Here's another example of an asymmetric wheel rim. So here the goal is to optimize several objectives at the same time. So the center of mass and the inertial axis so that it can spin stably. And we also optimize at the same time the strength to weight ratio under axle load. And yeah, you can just basically run this optimization and you can also 3D print it and test it. And here you can actually see yeah, the comparison, and they performs much better. Here's another actually quite a simple example. So this is a fidget spinner. So here we only looked at the mass properties, and we actually have 10 parameters to control the shape and the size of these handle holes. And as you can see with the real life demonstration, actually, yeah, does its job. Now, I want to move on a bit. So, while this is a very general framework that removes some of the headache around meshing, of course, several important aspects, such as, for example, how to handle topology changes or material interfaces are currently missing and also require more research. But of course, also another challenge is speed. And actually, how can we speed up the optimization? And I mean, adaptive refinement would be one obvious choice, but for much, much more efficient algorithms that basically really support interactive form finding, one would, I guess, need to change the strategy. And in the following, I want to focus on how to achieve interactivity by basically trading some of this generality with more specialized tools or more specialized focus. And I want to first focus actually on structures that are made of active band elements. So active banding allows the realization of really intriguing structures and has actually also very long history, playing a really important role in construction with very early examples, for example, from Turkmen tents. And yeah, I think it's fair to claim that this aesthetics from banding and band element, still fascinates designers, architects, but also mathematicians, because there's a lot of also interesting, yeah, underlying geometry in it. And yeah, a specific example from construction is, for example, this really beautiful pavilion from Achim Menges and Jan Knippers from the University of Stuttgart. Or also you can see it actually in bent glass used for modern buildings, for example, this Opus Dubai building by Zaha Hadid architects. And yeah, personally, I find this topic also exciting because it presents a very economic way of realizing intriguing shapes actually from flat panels, which are easy to make, easy to transport, yeah, and also pose interesting opportunities and challenges for deployment. So motivated by this, we started exploring how to design flat, flexible panels with some tailored mechanical properties that, when assembled, actually resemble a smooth shape. And in this example shown here, we actually developed a design system that actually tailors the mechanical properties of these spiral-like shapes, such that when you basically fold it together, you get your desired 3D target shape. And um, yeah, this system actually triggered quite some interest. And then actually with two partners, one from the University of Pisa, actually under the lead of Paolo Signoni, that many of you might know, and the other one is actually the School of Architecture at the University of Technology in Sydney, actually under the lead of Nico Pietroni, which also many might know. Ah, he's here actually. Oh, fantastic. Hi, Nico. We first of all, I mean, we worked together on already this system I showed before, and then they employed the system and also extended it to actually explore the design of innovative lightweight structures, such as, for example, this pavilion here. And the workflow basically starts from a parametric surface from which we analyze the curvature and place a cross field. And then basically a quad mesh is computed, and the software then automatically splits them into patches in sizes that are manufacturable. And basically here each quad contains a spiral shaped material element. And to ensure actually that this pavilion takes the desired shape in equilibrium, our software, what it does is actually tunes this parametric spiral-like shape. So this is actually under the hood. There is a differentiable data-driven model trained actually from offline FEM simulations, and it can actually predict all forces when the spiral is stretched, bent, or twisted. And yeah, then once such a configuration is found, basically you can give it a target shape. It tries to optimize the spirals. If you find one that works, structure can be very easily manufactured. So here with milling. Nice thing is it also fits conveniently to boxes for shipping and can be assembled on site, as you can see here. So these are actually Paolo Signoni's students from CNR that are assembling the structure. It's actually also a nice success by Paolo and also Nico. That this was actually shown at the International Architecture Exhibition, the Biennale in Venice. And here you can actually see how it's assembled. Yeah, here you see it fully assembled. Now, moving a step further, active bending can also be an appealing method. I mentioned this already a bit before, when used with glass. So in this project, which was actually collaboration with Helmut Poppmann, our motivation was to actually enable a new technology for designing glass facades that can be manufactured in an economic way, which is actually cold bending of glass. So cold bending of glass is a relatively recent method to achieve doubly curved shapes with glass panels. And it's based on the fact that actually glass can safely withstand certain mechanical deformation. So the idea is actually starting with an initially flat glass panel. We can bend it elastically to basically a pre-manufactured curved frame. And yeah, this method is much cheaper than traditional hot bending of glass, where basically glass is heated up and brought into shape. Because there, I mean, we also you need to shape each panel individually. As usually, if you have such intriguing facades, none of the panels are exactly the same. Now, however, of course, also working with glass comes with some challenges. I mean, glass is brittle, and so, so therefore, basically, this the shapes that you can achieve with cold bending, it's non-trivially constrained. And yeah, basically our aim was to come up with an interactive design tool that is suited for this fabrication method. Basically, it allows designers to quickly explore which panels can be achieved with code bending and which cannot. Show you this quickly first, the result. So yeah, our system basically allows to interactively explore these facade shapes, and it color codes which shapes require a hot glass building, so basically which cannot be cold bent, and which ones are fine to be manufactured with cold bending. And so architects actually get immediately feedback on the shape and also the stresses of the individual panels. So the prediction time for this is approximately 0.1 seconds for 1,000 panels, which allows now to truly interactively explore shapes and try to find shapes that are visually appealing. Now, these interactive rates, they're achieved basically because we trained a relatively simple predictor. So the model architecture is actually a mixed density network. The input is a panel boundary, and as an output, which might be a bit surprising, we do have two Gaussian distributions. And each of these Gaussian distributions, the mean contains actually the interior control points, which is the shape of the band glass, or defines the shape of the band glass, and the maximal stress of the panel. And we do have two shapes as output, because for a specific frame, one could actually have multiple stable states, which can look quite different. So therefore, yeah, I think it's actually really important to try to learn to predict both of these and not just one. And yeah, the probabilities here, they sort of reflect the likeliness of the shape. And what we do is basically we train this model on almost 2 million simulated panels. And if you would basically run these simulations on a regular PC, it probably would take multiple years. Yeah, and what I want to mention here is during the training process, we actually made two very interesting observations that actually, I would say, go beyond of just using a model to make things faster. So first, we realized during experiments that the network allows us to discover stable states that were initially not in the training set. So then basically what we do is we simulate these newly detected states to actually verify the observation, this is truly a valid state. And if so, we add it back to the training database, thereby basically iteratively improving the results. And I would say second, being able to predict not just one, but multiple stable states is actually a big advantage compared to a pure simulation-based approach, where it would actually, I would say, be fairly easy to basically identify one local minima of the deformation energy, but it's hard to reliably find both. Yeah, so I think here the advantage goes beyond just being faster. Now, I mean, this is also differentiable, so it also, because of this, supports quite straightforward shape optimization. And here is just one result I want to show you briefly. So by optimizing the design for fabricability, for example, by slightly adjusting the shape, in this specific example, one can drop the number of breaking panels, or basically panels that would be needed to be made from hot bending, from 1,500 to 900, while actually still staying, I would say, I'm not sure if the designer agrees, but staying reasonably close to the initial shape. And yeah, this results to this example approximately 40% reduction of the number of panels that would otherwise needed to be hot bent, and therefore allows for much more economic fabrication. I'll also not go into detail here, but you can also optimize for example, the angles of how two panels meet, so that you have like nicer reflections. And yeah, you see an example of this previous building that I've shown you. Okay, now with this, I want to switch gears a bit. So we have looked so far at designing with very specific material structures, for example, spirals. And I want to zoom out a bit and start looking at metamaterials a bit more broadly. So as you probably know, metamaterials are a very large topic of interest in science and in engineering. These are actually materials where its properties arise basically from this carefully designed structure of the material rather than its chemical composition. And in many domains, engineers are actually constantly searching for materials with novel, desirable property combinations. For example, I'm talking a bit from the architecture and construction perspective. This is relevant, for example, for designing very lightweight materials that are also stiff. They reduce the amount of material needed, for example, for building an object, or also reducing the fuel required for transport because it's more lightweight. Or a topic I'm very starting to become very interested in is tuning actually thermal conductivity. This could improve, the micro climate shaping capabilities of materials, leading to more sustainable but also more enjoyable spaces. Or also acoustic applications, for example, preventing certain frequency ranges from being transmitted through materials. Now, these applications are all very exciting, but they basically rely on our ability to effectively now discover and design a wide range of metamaterial shapes. And this problem has been, very widely studied. So there's a lot of related work on this, for example, including approaches to geometrically explore and enumerate topologies. There's also many optimization approaches, including topology optimization. But I would say basically they all either struggle either with a limited diversity of structures, or they face challenging nonlinear optimization problems, right? As soon as your objective, of course, becomes very nonlinear, it's difficult to optimize for structures. So we started exploring a bit if a data-driven approach could address this problem. And in particular, we tried to leverage a diffusion model to actually learn a latent diffusion model that can, basically guided by desired properties as input, synthesize the corresponding microstructure. And it turned out, and this one lesson I want to show you briefly that we ran into, if you try to do this naively, it's actually quite tricky to do. It did not work in the beginning. So basically what we did was we started by encoding the geometry with an autoencoder, and then visualized the latent space with color coding, actually the Young's modulus here, so the elasticity of the sample. And as you can see, this looks here very, very noisy. So which basically means that structures that are very close together in latent space could actually have very different mechanical properties. And this makes it challenging to learn the relationship between property and geometry. So um, one trick to overcome this, what worked well for us, is actually to incorporate some physical priors during the training of the autoencoder, enabling the model to basically jointly capture both the geometric and also the physical details. So here actually the idea is quite simple. So we basically encode the geometry as signed distance fields in planes that also provide and guarantee symmetry. And in addition, we also encode some displacement fields of the microstructure. So these displacement fields actually result from deformations under standard force tests. So they basically, in some sense, they encode the physical behavior. And by the way, also from those, we can quickly compute the homogenized mechanical properties of the microstructure. And if you use these together, turns actually out you get a much better latent space where now both similar geometry and similar behavior are basically grouped together. I think this is now also quite nicely visible in this plot here. And to see how well this works, we can now actually look at interpolation in this latent space. So here you can see actually two star models, which are truss structures with low Young's moduli and small volume fractions. And at the end, you see models that are plate structures, which have a high Young's moduli and actually large volume fractions. And then basically we just interpolated in latent space. And you can see here, I would say the interpolation works actually quite nicely. So these models retain um, initially their trust topology, then increasing the volume fraction to achieve higher Young's modulus values, and then gradually they transition into these plate configurations. Um, and we also plotted the path actually in material property space, which I think looks quite reasonable. And you can now, for example, use this to quickly synthesize optimal stiffness weight parts. So here you see a pillow bracket for which we actually ran a coarse optimization for finding the optimal material properties. And then basically from these, the actual material structures is the microstructures are generated on the fly and the model is printed. Um, yeah, now basically, this is nice, but of course, you know, to get to a latent model for microstructures, you require a database of training samples that do cover a wide range of available microstructures. And now, unfortunately, I mean, getting such a database is tricky. I mean, we cannot just scrape millions of samples from the web as you can maybe do with text or images. So we somehow we need to bootstrap the process by modeling them. And yeah, and I think this is not such a simple problem. So imagine, for example, you have to model all these microstructures shown here in your favorite modeling software. So basically, you would need to start composing elements such as struts, shells, and solids in a way to achieve interesting physical behavior. And yeah, this is hard to do. And actually, I have seen many students actually also in the, for example, material engineering side that actually really iterate months long over this. So we actually thought, an interesting central question is, what is actually a good representation for modeling this wide range of structures? And can we actually come up with a representation that allows us to efficiently design this wide range of structures in a more unified manner? So to address this problem, we came up with a procedural approach. The idea is basically, we came up with a graph-based representation and combined this with a, a new user-friendly interface that actually allows researchers to quickly model cellular metamaterial structures. And basically, what it allows you to do is it allows you to build metamaterials by composing various building blocks in a quick way together. So at a high level, basically, our approach uses a set of operation nodes to first define small skeletal pieces of the target structure, then apply a series of transformations like mirroring or rotations to basically fill the unit cell, and then apply thickening or other geometry processing operations to finally generate a physically realizable structure. Now, basically, conceptually, you can think of this as small compute graphs or programs with instructions that allow you to compute a wide variety of microstructures. And yeah, basically, I would say that the secret sauce behind this is to actually provide the right building blocks and geometric compute mechanisms to cover a wide range of structures, as you can see in a second. So here you actually see a few examples. So first, building a shell-like structure, then a shell plus a truss structure. Here you see a truss structure. And then also, you can also use this to actually create minimal surfaces. For example, you can see in a second, this Schwarz P, Schwarz D, or the gyroid. And yeah, I think this is in particular nice about the system, that you have this ability to actually create a wide range of such minimal surfaces, in particular these TPMS structures. So TPMS stands for triply periodic minimal surfaces. So they're basically independent, periodic in three different directions. So you can easily tile them and Also, they have these properties of having minimal surfaces, and this is exciting because uh, these or some of these are actually considered as the most promising metamaterial structures. So, for example, TPMS, they have amazing trade-offs between stiffness and density, so they can approach some of the theoretical upper limits. And they're also ideal actually for additive manufacturing because they're self-supporting structures. And yeah, for example, by now unlocking these variations of these TPMS structures, we can now do much more thorough exploration of these promising structures. Um, for example, we could easily generate structures and examine properties of weight versus stiffness trade-offs, designing anisotropic elasticity, or also we explored this for designing structures with phononic band gaps, so basically acoustic sound blocking abilities. Now, again, I want to take a step back. So basically, now with these, in some sense, we have unlocked precise control, but actually now creating them from scratch can still be labor intensive and does require expertise. So I think an obvious question is, can AI help us actually to generate these procedural materials? And I think in general, actually, this could be extremely useful because the concept of designing materials in procedural form is not just for metamaterials, um, but actually it's widespread in many other areas as well. Um, I mean, as you might know, right? I mean, it's like used for landscapes, plants, buildings, in urban design. Um, and one particular case I want to look at together with you is actually the application in visual effects, uh, where procedural material graphs are widely used for actually appearance design. So there, basically, they allow you to model and describe how a material, such as, for example, marble or wood, looks like, what texture it has, and also how it reflects and interacts with light. And these are basically node-based, so meaning you can actually control every aspect of this texture, such as color, roughness, reflections, and bumps procedurally. It is really, really cool. And if you have a good artist, I mean, they can create incredible materials with this system. So you can have, things that look mossy or rusty. Um, and then one nice thing is, of course, you can apply this to an arbitrary 3D shape and texture, basically 3D scenes. However, as you can see here, these material graphs can become quite large and complex. So this is the graph for this rock-like material here. And yeah, you need to be a really good artist, right? That you're able to actually design something that then looks exactly as how you want it. So therefore, we started to investigate if we can actually generate these graphs from pictures or text descriptions instead of creating them manually. And in the beginning, we just tried naively. Maybe we can just ask a vision language model to do that job for us. So we tried this. So basically, we gave an image, and then we prompted a model and basically asked, please create a Blender procedural material using Blender's Python API to match the appearance of the image when rendered on a flat surface. And we tried this, but unfortunately, this was the output we got. So you can see actually, this does not look the same at all. And I guess the very likely reason for this is this fails because these procedural material programs, they're very domain specific and very much underrepresented in the training data of this vision language model. So to solve this problem, basically we create a fine-tuned a VLM to actually predict procedural materials, and yeah, basically takes as input an image, then produces code and executes the code in Blender, then yields actually the shader node graph of the material, which is then rendered on an image, as you can see on the right-hand side. And yeah, once again, also what I mentioned before, I mean, if you want to now train such a model, you somehow you need data. And I would say this was the main challenge here. And yeah, and also, I mean, this challenge you have it basically almost anywhere, right? Where you want to do something domain specific that you don't have enough data. So I think in general, yeah, an important question is how can we actually develop effective data augmentation strategies? Now here in this project, our strategy was to actually leverage the pre-trained vision language model to perform data augmentation. So basically, the idea is to take a random sample from the training database and then use the reasoning capabilities of the large language model to actually generate new programs from that example. And I guess the key here was, that we did not just do basically random perturbation on the graph, but actually in some sense, leverage the generalist knowledge of the vision language model that knows, for example, how Python program is structured, and therefore the likelihood of a reasonable program augmentation is much higher. And then you can actually, of course, check the validity and quality of the material. And if the material is of high quality, then you can actually, add that basically newly discovered material to the training database, and with this basically grow your database. And with this, we managed actually to go from only 800 materials that we had in the beginning to more than 500,000 samples. And yeah, with this, we were able to get the system running. Here you now see a couple of tests. So these are photographs of different materials as input. And here you can see actually the matched output. And the match is not absolutely perfect, but I think it's actually quite close and does resemble the structure of the material. Now, just want to show you two more projects very quickly. So far, basically, we have used these vision language models to generate material graphs. And now going one step further, one can ask, for example, can these vision language models also be useful for directly generating fabricable 3D models? And as a first use case here, um, one of the students I collaborated with, Kenji Tojo, he started looking at how to generate 3D wire art from a concept given as an image or words. So for example, from these input rows, we would love to actually get the 3D wire rows on the right-hand side that is also manufacturable. The challenge here is actually how to go actually from a very abstract concept to something that you really can build that also respects the necessary fabrication constraints. And also, the wire model is actually a very abstract representation of the input, so there is no one-to-one blueprint you can follow. So to just give you very quickly an intuition of how we solve this problem, actually we started with a random 3D curve, in this example here, with the text input shark. And now the key problem is actually that we need to know how similar is this 3D curve to a shark. And basically to answer this, we just use a vision language model, which can capture the semantic meaning of what is in an image. For example, how likely it is that you should see a shark. And also, I mean, this model is differentiable. So we can actually now start changing this current 3D wire model iteratively so that it gradually starts looking more and more like a shark. And yeah, with this system, I can now show you briefly basically what the optimizer does. So you see basically starting from this random curve, it actually does, converge towards a wire shark. And here are some more examples. So this is a multi-view wire art generated from text prompts that we actually also fabricated. So the input here were cat from one view, dog from another view, and bird from a third view. Now, yeah, I mean, of course, this is a more artistic application, but I'm excited about it because we're able to show a new way of basically using generative AI to create actual things by also solving I would say, a challenging design problem that involves both some perceptual constraints And we had this in there, via a vision language model and physical constraints. By the way, I did not talk much about the physical parts. Basically, there is also, yeah, simulated also so checks certain constraints. For example, that um, the bending angles are not too high. There's also some checks that you, um, yeah, basically have a good chance of fabricating these models afterwards. Yeah, and then one nice thing is, I mean, there, of course, there was no custom trained ML model for wire art. So we just leverage this very generic vision language model that understands the correlation of abstract concepts in images, and then we could actually extract the relevant information to design the 3D object. And yeah, I believe this concept is very generic and probably can be applied to many other application areas as well. Yeah, in particular, I think for design and in architecture. Now, the very last thing that I want to show you before wrapping up, this is actually some very recent work that was just accepted to ECCV. Here we also went a step further and try to see if we can somehow also do something with video models. So probably all know, right? These vision models, these video diffusion models, they have advanced, like crazy over the last uh, 2 years. And I guess we're all, stunned when we saw, for example, these videos from OpenAI, what Sora can provide in terms of temporal consistency. Um, so basically, based on this, we asked the question, can we maybe, and I work a lot with architects, can we use them to basically simulate urban wind flow? And we thought actually maybe the problem is sort of similar. So basically we have yeah, a similar framing. So basically there's a projection onto the horizontal plane. There's basically a velocity field, and that evolves basically as a frame, as a sequence. And the idea was basically, so we start with a pre-trained transformer-based latent diffusion model, um, and then yeah, basically want to apply it to wind fields. Now, if you just do this directly, right, it doesn't work because there's a pretty big domain gap between um, yeah, what you would like to see and what the video model was trained on. But actually, it turned out that you can actually quite easily, fine tune this general video model, and with actually, quite reasonable amount of data, because it also, in some sense, it already, has an understanding of how things move, um, and then apply this to these wind fields. And what we basically did was two things. One was we fine-tune the decoder weights in this encoder-decoder structure. Um, so we have a data set of 13,000 simulations, and we also had added some physical loss prior to basically have a divergence penalty to enforcing incompressibility, and also making sure if you have a building layout that basically, yeah, things don't flow into buildings. And this gave us much better also reconstruction quality. And then also we've basically fine-tuned this diffusion model conditioned on the urban footprint and wind speed and domain size. And this then basically gave us a surrogate model for urban wind simulation, basically producing full velocity fields over more than 100 frames in under a second. And yeah, also, if you use a differentiable rasterizer, you can also make this whole machinery yeah, completely end-to-end differentiable. And with this, for example, also start moving around or optimizing building layouts. And as I said, I mean, the main application we're interested in is in urban design. So it actually really matters, the layout of buildings, how it affects the wind speed through it. And you basically want to prevent two things. I mean, you want to prevent that the wind speed is too high, because it creates, very unpleasant experiences. And I know, for example, I lived for a long time in Vienna. There are some parts in the city where, yeah, because how the buildings are aligned, there's extremely high wind speeds. So you can even like, if it's very windy, yeah, you don't even want to go out on these streets. Whereas in other areas of the city, it's completely fine. And the other thing which you also want to prevent is that, also that you don't have any wind speed. So basically, if things are too much locked in, then maybe pollutants, accumulate, or also that these areas get too hot. So basically, you want to find a good trade-off. And yeah, you can basically now just use this model to very quickly evaluate a certain layout. And as I said, because it's also differentiable, you can ask the system to maybe move around buildings to find a better trade-off of these objectives. With this, I want to wrap up. Sorry, I'm 5 minutes over time. Is that okay? Um, good. Yeah, I want to conclude. So just to, first of all, quickly summarize, yeah, I've shown you various flavors of design workflows, starting from traditional CAD tools, supporting optimization based on explicit constraints and PDs. And then we looked at some interactive approaches, which allow to keep the designer in the loop and interactively explore design trade-offs. And they are basically surrogate models allowed us to predict complex material behavior, such as, for example, the bending of wooden spirals or the shape and maximum stress of glass panels very quickly. And then we shifted focus and started exploring diffusion models and vision language models for tasks such as metamaterial design, procedural materials, and also these wire sculptures. And still, basically, with all of them, we had physics-based simulation as an additional ingredient. And with this, we managed to either increase the robustness or also ensure constructability in the real world. But also at the same time, we were benefiting basically from these, being able to, in some intuitive way, basically use text, for example, or image prompt to design to drive the design process. Now, again, taking a step back, basically when creating design systems, you're very often motivated by this goal, and actually started with this motivation that we want to become more efficient. And I would say, actually, looking back, we clearly have seen strong efficiency gains, and especially now also in general, if you look at it, with the success of large language models and generative AI, the acceleration we see is really, really incredible. And what we also see in general is a very fundamental shift from basically how to do it to basically what we want to achieve. And I want to explain it a bit more in detail, particularly looking at software engineering. So I think this shift is probably most prominent at the moment in software engineering. So there basically this gap between traditional software engineering and AI-based coding, it has really widened a lot from being just a nice tool that makes you a little bit faster to a very fundamental shift in philosophy, where basically we moved from instruction-based development, so basically telling a computer how to do it, to an intent-based development, where basically we tell the computer what we want to achieve. And yeah, this allows entering really this area of massive expansion ratios. So basically a human can very easily write 50 words of text, and then the AI generates thousands and thousands of lines of code. Yeah, and now, as I said, I would say, and I also see this at Google and many other companies in software engineering, this really has fully arrived. And there are studies that basically now say, in terms of adoption, there's more than 90% of the developers in Fortune 100 companies are using AI-based intent tools, and also in terms of volume. So in now full stack environments, AI-generated code is estimated to account for now more than 50% of all new commits. And I'm just wondering now, what does this mean for architecture, engineering, and construction? So there, I mean, the adoption is slower, but it's of course also changing the industry. And I think an obvious question, in my opinion, is there anything we can learn from software engineering for computational design and the areas it's applied in, for example, architecture engineering and construction. And I think at the first glance, things maybe at a high level are not so different. So you can maybe think of CAD and BIM, so building information modeling. Um, these models, they can be viewed as in some sense as some specialized programs, right? Or more accurately, parametric programs that define a build asset. And we can, of course, try to leverage and build on the developments in code generation. Now, and basically also with this, moving up the abstraction ladder. Um, Now, basically, what does this mean for AC? So what I see in software engineering is actually that the focus starts a lot, from programming to actually shifting towards writing extremely high quality design docs. So basically, once again, defining the what. And this is actually much more than simple prompt engineering. So high quality design docs, they really require very deep engineering skills because they function sort of as a mental simulation of the system. Um, and as an author, right, you have to anticipate edge cases, navigating also complex architectural trade-offs, and also basically debug this design doc itself. And yeah, I'm wondering a bit, I don't have an answer, but basically what would be the equivalent of a good design doc basically for AC? So maybe, more thoughts need to go into abstractions of representations and also design interfaces. Now, just as a last word, I think also, there are not just similarities, but there are also very significant differences, of course, between software engineering and the AEC sector. So for example, in software engineering, code becomes more opaque, but it can be very easily updated. And, very obviously, we cannot afford to do the same for building processes and build assets. So they're just, to also give you a bit context in the built environment, of construction operation of a building, it's, for example, responsible for approximately 40% of the global carbon emissions. And maybe unlike, the energy bill of a house, which you can change by installing some solar panels, the carbon emitted to make the concrete, for example, for a bridge is basically locked in at the moment that this concrete cures, right? Um, and so, yeah, to basically fix this, we have to think, differently probably about design from the very start of creating these structures. Um, so yeah, so probably the ultimate goal is not just do the same with increased efficiency, but rather helping designers to deal with complexity. Um, and again, like this EC perspective, I think we have to design very differently from the start. So basically using different materials, um, maybe timber, low carbon, green cement, or also think more, for example, about retrofitting of old buildings instead of just knocking things down. Yeah, also thinking more about circular construction and allowing reuse. I think this, has of course huge potential for impact on society and how we live. Um, yeah, and just maybe one final word. If you want to go beyond also these optimization-based approaches that I have touched on, basically truly leverage AI system for this, I think it also, we need systems that basically go beyond pixels. So they're basically physically grounded, they can reason in metric space and allow simulation and interaction. And yeah, as a researcher, I'm of course excited about all of these opportunities because it allows us to truly rethink design and design workflows, and with this, of course, also impact the world around us. Um, yeah, with this, I want to end my talk by actually thanking my wonderful collaborators, students and postdocs that actually have enabled this work, as well as my colleagues. And yeah, I want to thank you very much for your attention, and sorry for going over.
Thanks. Thanks for a very nice summary about this work and also for time talk and discussions. I guess we can cooperate in that time for our questions. Thank you for this wonderful. I have a very good question more
Um, so basically, I so I mean, in our system so far, basically, you can basically just design, one cell, right, and then basically, tile this. Um, we so in that procedural world, we have not, and I guess it's very interesting future work. I mean, we have not thought, too much about how to basically connect the different cells, right? That you get basically interesting variation. Um, I mean, what you definitely can do, and this is maybe the work I've shown before. So once you basically use the machine learning model there, so there you actually saw quite a bit of variation in the metamaterial structures itself. And there, of course, you have constraints to ensure that they're properly connected. Yes, so there's basically some energy making sure that the boundaries can match. And also, by the way, one very interesting thing to think about is basically, I mean, once you have a cell, right, that is tiled, you can also shift around basically the representative volume to also try to find better matches. Yeah. Yes. I mean, yes. I mean, usually how we try to operate is basically by trying to collaborate or work with the domain experts. So it's basically in a first step. Yeah, we try to get a bit inspired, right, by basically seeing what are they struggling with, um, and yeah, and then hopefully by giving them these tools, yeah, allowing them basically to yeah be more efficient, right, or maybe discovering solutions that were difficult before, very difficult to do or discover by hand. You can actually maybe almost like Nico would be the better person to answer this. I mean, you have seen when milling it, right? There are like numbers, small numbers milled on it as well. Yeah, you definitely need this, right? Otherwise, there's no chance. But maybe, yeah, Nico, do you want to say something? Yeah. Maybe we need an XR system or something to guide. Yeah. But yeah, maybe in general, actually, not just with this project, but with many other projects as well. Actually, the assembly stage itself often actually gets overlooked. And for example, also just to have the connections properly working, right, was actually huge amount of work. Um, yeah, and I mean now also working a bit with um, architects and people on the construction side. Yeah, basically how to deploy a solution is actually probably, I mean, for many things, actually, the biggest hurdle. So there's many things, they're basically nice on the research side, right? But then if you really want to bring it into practice, so that it gets applied, yeah, these are very relevant challenges.
Um, much about the retirement of the So, as service is heavily rely on uh, contractors integration and in others example. So how do you think it's possible to extend it to some problem response information and it's like finding new materials? Is it possible to extend it to that or think of some other components?
Uh, I mean, I hope I don't tell nonsense, but basically, I mean, I think extending to nonlinear materials, I mean, if you have the proper basis functions, that should be fine. And I mean, we even had also in our paper, even like some example with nonlinear material models. Yeah, so I, yeah, I think that is not a challenge.
Oh,
Yeah,
thanks.
I, yeah. But I'm also, I have to say, I'm not, the world expert on XFM, so I hope I. Yeah.
We don't have options. Sure, right here. Functions to chat or doing incorporated, that's great. And here comes to the next is because and let's see your name.
Yeah, uh, is this yours? No, answer it for you. No, thanks for raising. Yeah, good job. And lots of top, lots of width of your research. I'm impressed. Uh, yeah. Universal. Ah, schön. Everything. You are Universalgelato in all this stuff. Well, the engineering is almost very, very. Yeah. Yeah. I reduce this emoji. I like, there are so many papers. I'm like, wow, that's so interesting. And then it comes to the solution. Ah, they have an emoji. Exactly. It's like, okay, uh, in my coworkers, sorry, I'm just gonna test. Uh, yeah, I'll talk to you later. Slideshow. Uh, not yet. Is it because there are two cables? I have. Ah, now it's happening. It's happening. It's happening. Yay! Okay, it's working. So you want this? Okay, you can just close my laptop. Put yours on top. Make a like.
Yeah. So there's HDMI.
Uh,
Sure, you want this? HDMI. Okay. Can you use this one? Okay. Ah, okay, it works. So when I connect this, I press this after that, is it? HDMI okay. This large okay. One and for the other HDMI. Yeah, okay. So I just connect and then switch this. That's it. Okay. Exactly. Thank you. Okay. No problem. Oh, sorry, I don't see on this one. I have one. Hold on a moment. You can take it down. Thank you. Yeah, yes. Clear. This one. Um, Change the configuration of display. And could you get me the start? To get this one. And just a version, and now I go take it down for next this one and this one. This one. Yeah. This one and thread console and smooth also this one. And there is a mouse also here or no? It's a pointer. I will try. I can. And and the mouse, there is no mouse. There's okay. touchpad. And how? This is- this is just pointer. Temporary. First I need to open it. Okay. Like this, pressing this goes to next slide. Ah, I will need only to the change and to yes. Yeah, this point to this one. Ah, I want to use only this one in case, and for me, three, I might use myself. Yes, it's completely up to you. So you will have me enter the start to get it. Okay, that's thank you. Ben böyle bırakıyorum. Tamam bırakıyorum. Bakmana gerek yok. Bir şey yapacak ya bizim. En son. Ama şu şeyi açık, şu açık. Ha, hep yanlış şu olsun. Yok, şu ya, tamam. Şu dursun diyorum. Ha,
The- Ah, okay, okay. Thank you. Yeah, yeah. Thank you. Okay. Can I test one of them and see how close I need to hold it to my mouth? I want to. Hmm? Yeah. Yeah. Test, test, test, test. Yeah. Hello. Okay. Here we go. Okay. Yeah. And I can turn it off with this button. So I can switch if I. Yeah, it's turned off. Now it's on. Now it's off. Nervous. And once I finish, I will put this back here for the audience. If I use it. Let's see. Let's see. Okay. Thank you very much for the introduction and welcome to this talk. This is a project that happened in collaboration between ETH Zurich and TU Delft, and it's called Gravitet, a fast multi-grid hierarchy construction for tetrahedral meshes. Let's get right started. So we walk around Istanbul and we meet this octocat. And the first thing that comes to my mind is, can I tetrahedralize this and then solve a heat equation on it? So this cat is now not just a surface, it is a volume full of little tetrahedra. And typically when you try to solve something like this, a PDE with a Laplacian on a volumetric mesh, you would instinctively first try a direct solver, but direct solvers scale poorly. And when you have volumes, you get a lot of vertices on the inside. So the scaling becomes quickly very expensive. And the state of the art that often a lot of people use is called Holmot, for example, a sparse optimized solver. But even that will struggle poorly when the resolution goes into the million. And the first question we have is like, oh, is there a way to do this faster? And there has been for a while. These methods are often called multi-grid methods, and they operate by working on different resolutions. So you have a sparse symmetric matrix system, and it's just AX equals B, and A is a sparse symmetric matrix, and you leverage the computation, like different methods for different resolutions. So you can focus your computation on the high resolution details using something like Gauss-Seidel iterations, which converges poorly globally, but converges well when you just try to reduce the high frequency error. So you go to the high resolution to reduce the high frequency error using Gauss-Seidel, and then you go to the medium resolution, and then you can focus on those frequencies to resolve. And then you can continue this until you go to a very low res, and there the scaling problem that you had at the beginning with the too high resolution to use a direct solver doesn't happen anymore, and there you can use a direct solver. And generally in multi-grid methods, you then want to communicate between these different resolutions. And the basic algorithm is called the V-cycle algorithm because you travel down and up and then down and up and down and up again, this hierarchy, and you pass on the residual, which is called residual. It's basically the error. You pass it down, you solve it, then you pass it up again. And the main ingredient for a multi-grid method is the so-called prolongation matrix. The prolongation matrix tells you how to map the values of one level to the next level. And also the transpose of the prolongation matrix tells you how to map the higher level to the lower level again. So it's basically interpolation, extrapolation. And it's a series of matrix, one matrix for each level transition. And if you take the original matrix system, you can just slap on the left and on the right a prolongation matrix. And then you're reducing your big matrix to a smaller space. And then you can continue working on that. And you do this for every level. So the key ingredient is prolongation matrices, and they are not unique. You can have many different multigrid methods giving you different prolongation matrices. And some of them can be like designed to just have very few levels. You can have a lot of levels of hierarchy. You can have different weights on how you represent the higher level on the lower interpolations. And there's a lot of freedom to do. But generally, there is also a lot of difference how fast these algorithm converges based on how good your choices of these prolongation matrices are. And this is what we want to do. We want to find good prolongation matrices. So we have a 3D volume that we want to use multigrid on. And there are different approaches to deal with 3D multigrid. Very basic, popular, and awesome are grid-based methods, but they are not suitable for representing the curved surfaces when you are reducing the resolution. So on your high-res resolution, you can use a lot of cubes to represent your curved surface, but then you go lower, lower, lower, lower, and at the bottom, you still want a good representation. And this is not going to fit well with cubes. Next are graph-based methods. So they use the connectivity of the mesh, and they're already much better. And also our closest related work is going to be a graph-based method that we're going to work with. But generally, they will, as we will show, converge slower. And then there's a third class that is directly designed for tetrahedral meshes. The problem is that they work mostly on edge collapsing and then repairing the broken tetrahedra that you get once you collapse. And we do not compare against them because they take hours for the meshes we are trying to use, while we are trying to build the prolongation and solve it within seconds. So what we want is fast construction of prolongation matrices and good convergence. And yes, we can actually do that by introducing our new method, Gravotet. Gravotet means graph Voronoi tetrahedral multigrid method. And it's a fast and effective coarsening strategy. That is the idea behind it. And it starts by having a prioritized sampling of what vertices do we take into the next coarse level. After that, we focus on the surface, because the surface is where we have more details, where the boundary condition is supposed to survive. So we give the surface extra attention. We do a approximately Delaunay connectivity on the surface. I'll explain that soon. And then we continue to the interior. Once the surface is established, we can then connect the interior of the our subsampling, our hierarchy. And after we have done that, we have like a set of tetrahedra, and then we can compute the barycentric weights to actually get the prolongation matrices. So let's go into some details. The prioritized fast disk sampling, we do it by first computing a feature on every vertex. So for example, a corner of the cube will have a strong variation of its normal around it. And then we give it a higher value because of that. And then we will sample it first. This will be a prioritized vertex. We call it like, oh, this is an important vertex, so we should make sure it doesn't get lost during the sampling. So edges of a cube would survive, or tips of the ear would survive this way. And then we sort all the surface vertices by these features in order for the fast disk sampling to then start with the important vertices. And the basic method of the fast disk sampling is take a vertex, build a radius, and instead of querying for the nearest points, we simply look at the neighbors in the two ring at max. And then if a vertex is too close, we say, no, remove you, go away, shoo shoo. These red marked crossed out vertices will not be part of the next coarse level. And then we continue this. We take the next vertex, we look at the radius, we start removing more vertices. And this is very fast, linear time. And speed is something that we really need in order for our goal to be reached, to have fast results. So we end up with 5, in this example, 5 coarse vertices that go into the next mesh generation. And an added bonus, because we sorted the important vertices first, and then we sampled them first, the next coarse resolution already has the same ordering preserved. So the important vertices stay in the front for the next generation after. And now to the core idea. We have heard this now plenty of times. Voronoi diagrams dual create Delaunay connectivity. Delaunay connectivity is our favorite type of connectivity. It makes very nice meshes. But getting actual Voronoi diagram Euclideanly takes some more effort. And we avoid that effort by going for a graph Voronoi diagram that we can quickly compute using the connectivity we just had. And then we just take the dual of that and assume that this is good enough. It's not going to be perfectly Delaunay, but we will see that the properties it has in its barycentric weights are good enough. I mean, actually very efficient for multigrid method. So how do we do this? The clustering part now. So we have these orange vertices. We want to connect them with each other. And a straightforward way to do this is to look at the fine vertices, so the green ones, and look at where are they connecting. If every green vertex has a closest coarse orange vertex, and if 2 green vertices are connected that belong to different coarse vertices, we connect the coarse vertices. So it's something you can do fast with Dijkstra's algorithm, and starting multiple locations at once. You can quickly scan which vertices belong to which coarse mesh and coarse vertex, and then connect them with each other, and then you get something like this. Also very fast. And we start by only doing this for the surface vertices. So we had sampled all the vertices with prioritization for the surface, and then we connect the surface vertices, and then only after that we go into the volume. And the reason why we're doing this is, if you don't, then you end up with this type of mesh, and it should make you feel weird in your stomach when you see it, because the surface is all blah, blah, blah, because it wasn't taken care of, prioritized. And this is why I'm doing the other way. We get this nice surface, and we need the nice surface on the coarse resolution because our boundary value problem is defined on the surface. And if the surface at the bottom is all mushy, then we cannot expect good convergence of our solution. Once we have that, so imagine you had all this in 2D. Now we can go into 3D. So the surface will now grow into the interior of the volume. And with the exact same connectivity rules, we just continue, and then we have all the vertices connected. And then we want to compute the prolongation matrix weights. So what we do then is we look at the coarse vertex connectivity. We look at every fine vertex, for example, this green one, and then we ask, in which tetrahedra are you inside of? And that's a quick test of looking at the neighboring vertices, finding the coarse vertices, and checking, are you inside of it? And then you take the barycenter coordinates of the green point relative to the tetrahedra that it's inside of, and those will be your prolongation weights. So those are the parameters of interpolation that you then use in your multigrid steps. And notice, though, that because we used a graph Voronoi, we're not actually getting exact tetrahedra. Many of them will be fine tetrahedra, but they may overlap, and they may even collapse. And it is actually okay. Don't be afraid of collapsing tetrahedra when you're doing only barycentric computations. You're not computing the inverse mass matrix, because that would explode, but you're just having a tetrahedra that might collapse into a triangle, but the barycentric interpolation is still reasonable in that. So, and then this is a repeated. So we do we do this once to get to a lower resolution, and then we can do it again to get an even lower resolution. And generally, we stop once we are below 10,000 vertices. And the tetrahedra that come out are all reasonably shaped. They are nicely spaced away from each other because the vertices were selected using fast disk sampling to be in a nice distance from each other. And then we can run our algorithms on this. So for example, 500,000 vertices in the input, and then we can compare our method together with, wait, this is the green one. This is a graph-based method, and these are the other two ones are algebraic multigrid methods. The algebraic multigrid methods only care about the matrix. The graph-based method, oh, sorry. Okay, I shouldn't use this. The graph-based method uses the connectivity of the mesh, and then our method uses the barycentric weights. And we see from the total computation time that the actual build time of ours is bigger. Takes more time to build up, but the solving time, it's much faster. And this is sort of the benefit of having better prolongation matrices, putting more attention into building them. And then the direct solver at this resolution is still competitive for Poisson problems. Then we can look at biharmonic problems, which are inherently more ill-conditioned. And there we can see that our method's added convergence quality is really beneficial for this, while the other methods really struggle to get anywhere close to the tolerance. And the direct solver still holds up for this resolution, but we can now up the resolution, like, oof, give me more, give me more. And we end up, for example, with 2.8 million vertices as the input TET mesh. And then our method still continues to do well for the Poisson problem, while the direct solver fails because it's very memory intensive and scales poorly. It already starts to fail on my machine at 800,000 vertices. And then the graph-based method is still doing fine, but then let's look at the biharmonic problem, and there the competition stops. Most methods really converge poorly or would take almost forever, while the direct solver also has no chance for this resolution, and our method still holds up. And as you can see, most of the computation time now goes into the solving itself. The buildup is now minimal. Yeah. We have tested this on plenty of meshes for performance. And in generally, after 100,000, 200,000 vertices, our method starts to beat, not just in build time, but in total time. So this is important because a lot of multigrid methods are designed to solve faster, but the build time is sort of considered to be separate because they think of, oh, I want to run a thermal simulation, so I only need to build once and then I solve all the time. What I'm presenting here is something that where the build time with the solver time is actually together very nice. And for the biharmonic problem, the competition ends earlier. Many methods time out, or the Holmot has problems. Direct solvers fails at already 800,000 vertices. And yeah, that would be my presentation. I have more slides, but I had some time pressure. And you can ask me about mesh quality and ablation study and sparsity if you want to. Thank you very much. Yes. Wow, what a great question. I love it. Let's look at the mesh quality. So here you can see two examples, the armadillo and the fertility mesh that I used in the presentation. Laser. Yes. So the red curve is the input. It was generated using TETGen because FTET just couldn't finish at that resolution. So I stuck to TETGen, and you can see, okay, the minimum dihedral angle, yeah, this is a good quality mesh. And once you do the method apply, you get these orange, green, blue, these other curves, and they all look quite similar. They all have more of the very thin slices, but consistently. Like if you continue the algorithm, it doesn't keep moving to the poorer and poorer quality. And here on the right, we see the aspect ratio. So some of them are like super thin and then they explode here. But generally, like, yeah, the red ones are better. And then we shift a bit to the right and the aspect ratio, but it's not too bad. Here are some more examples if you want to see, including Istanbul Octocat. Great. Wonderful. I love it. How fast does the solver converge? Okay, let's go to, yeah, it's an iterative solver. So here you see the time. So first you have the hierarchy building. This is the building of the prolongation matrices. This part is so small that you cannot see it, but here you have it, 10 seconds. It's the same for the Poisson and the biharmonic problem. And then you have this 29 seconds. This is the setup of the hierarchies. So remember that for the multigrid algorithm, you have to multiply some matrices together. That step takes some time as well, but you only have to do it once. And then after you have done that, you just do the iteration, V cycle, down the resolution, up the resolution, down the resolution, up the resolution. And this is the time that goes in here. So for 2.8 million vertices, the biharmonic problem on this fertility mesh took 36 iterations. So these are the dots that you see here. And the total time is 164 seconds, which is about. So to us, so comparing to the others, the biharmonic one was the hard problem to approach, while the Poisson problem was the easy one and the more common one. So we wanted to go for the biharmonic as well because this is the harder one. I haven't tried even harder problems than that. But notice also that for the biharmonic problem, the relative residual is like the target is 10 to the minus 5, while for the Poisson problem, it's 10 to the minus 8, because people usually are sufficient when they try to solve the ill-conditioned problem with less accuracy. Okay, pleasure. Ah, good question. That actually was a problem in the paper. Uh, that we had a input mesh that we wanted to TET-gen, and then the mesh was broken, which I didn't notice. Then the TET-gen was broken, and then there it didn't converge well, and it took forever. And I was like, "What is going on here?" And then I had to repair the mesh first to make it watertight. But generally, I relied on TET-gen to get these high-resolution meshes, and trying to add some noise without inverting something was, yeah, not valid. Yeah, yeah, yeah, yeah. Yeah, that's true. True. So the input mesh is the only input like quality TET mesh that we care about. And if that one is broken, then the Poisson problem is broken as well, because then you have these negative masses, or the mass matrix has these extremely large values. So I haven't, like, I trusted TET-gen, but if I imagine that we would now break one of these TETs, then we couldn't expect any of the solvers to work on this. So my answer would be, yeah, we have to, by baseline, require good quality TETs.
Seven. Jeez.
Okay. Hello, everyone. I'm Serkan Demirci. I'm a graduate student at Bilkent University, and I'm going to present our work, direct volume rendering of tree-based tetrahedral adaptive mesh refinement data. So, first of all, some prior background information about direct volume rendering. So, when we talk about direct volume rendering, what we are trying to do is to convert 3D volumetric data into a 2D image directly from the data without creating some intermediate surfaces or some other types. And when we define volume, everyone knows we can say it's a quantities or defined over a 3D domain. So when we for that direct volume rendering, there is usually two steps. First one is the sampling. Sampling means that we take we acquire the scalar from a position. Then we use classification where we take that scalar and convert it into a color and density value. There are many different rendering algorithms, but the ray marching is well known and simplest and common one. So in ray marching, we take some fixed steps throughout the volume. Then we take samples, map them to colors, then composite them into a color. And more recently, we have is starting to get more popular is woodcock or delta tracking. So for woodcock or delta tracking, we have it's a Monte Carlo's integration method. So if it's a homogeneous volume, we know how to solve it with Monte Carlo integration. But it's not usually, the volumes are not homogeneous. So what we do is we pretend as if homogeneous by adding some fictitious particles. Then, so our volume becomes a homogeneous volume with a maximum density becomes this density. Then we randomly go based on the maximum density, we sample some distance and go there, take a sample. Then we say, what is the probability of that particle being the real or fictitious particle? And using that probability, we decide, we actually throw a dice and we decide whether we call it fictitious or real particle. And if it's fictitious, we continue because we didn't hit anywhere. If you decide we hit a real particle, we return its color. Similar to many delta tracking methods, similar to many Monte Carlo integration methods, this method usually is much faster, but requires many samples to be taken and averaged. So we get some color value and we apply this process over and over again, and finally it can, when we take all averages, when we take the average of all samples, we in the end get we converge to unbiased, correct solution. So again, to repeat it again, when we say volumetric representations, it's a quantities defined over a 3D domain. Most commonly used representations are structured mesh, unstructured mesh, and adaptive mesh refinement. Structured mesh is the most simplest one. We divide the domain into a fixed size voxels, and however, it has some problems if the volume is too not homogeneous, and if some part of the volume requires high frequency features and other parts do not, we waste some memory and computation over them. Also, for simulation, if we use structured mesh, it doesn't conform to the domain, our domain. So that's another problem. So unstructured meshes are another method. So we divide the space into polytopes, usually tetrahedra or hexahedra, and we use that to perform the simulation and or represent the volume. So unstructured meshes are good for representing the input simulation domain or geometries, but again, they do not adaptively refine when you do the simulation. And adaptive mesh refinement is similar structured meshes, but we start with a coarse mesh and we progressively refine some cells. And adaptive mesh refinements are good for progressively refining it during the simulation, but they do not, again, follow the input geometry for simulations. So to solve these two problems, like one is the try to conform to the input geometry, and the other one is the try to adaptively refine the volume during the rendering. Holke proposed AMRs with general element types. These have some coarse unstructured meshes, then they are refined progressively. So in our work, we focus on tetrahedral AMR meshes, specifically TET-AMRs. So it's composed of an unstructured TET mesh, where each element can be further recursively refined into 8 children. So it becomes a forest of refinement trees. Each coarse element has a tree, essentially. So we get, during the simulation, we refine or coarsen the volume based on the our simulation criteria. And one thing good about this structure is that so you don't need to store all of the vertices of the finer levels because they can be deduced from the coarse mesh. So Holke only stores the coarse mesh and some compact lift descriptions that can be used for recalculating the vertices. So there are no existing rendering methods for directly rendering theta-MR. One method to render this kind of data type is to convert it into an unstructured mesh. However, this means that we are adding new vertices and we are increasing the memory size. Also, we are losing the hierarchical information for the volume. So in this work, we proposed direct rendering of theta-MR data. We realized this rendering with two methods, Ray-matching and woodcut rendering. And we proposed some refinement tree traversal methods. And instead of generating the vertices, we on the fly generate the vertices as we traverse the finer levels. And since we have a hierarchical structure, unlike the unstructured converting to unstructured mesh, we can do some performance improvements. We experimented on two methods. One is coarse mesh macro cells. The other one is the view-dependent early tree traversal terminations, which is something similar to level of detail. Okay. So we start with the preprocessing. Unlike Holke, we also stored the non-leaf element descriptions because it's faster to rendering for that. It's faster to rendering that way. Also, we reorder the elements in pre-order arrangements to again speed up the rendering. Also, the child orders we changed a little bit. So when we are talking about rendering consists of two stages. The first one is coarse mesh traversal, where we traverse the coarse mesh one at a time. And we, using a rendering algorithm, we decide where to take samples, and we take the samples. So to take samples from that volume, you need to go down to the leaf element and create the leaf element vertices and interpolate the vertex scalars. So for that, we use refinement tree traversal. So for, again, coarse mesh traversal, we use hardware BVH over the tetrahedral faces. This is for modern GPUs that have the ray tracing cores. So we can offload the work of finding the next tetrahedron to another core during the rendering. So it's faster to do it this way. Also, for that, we send two rays. One is back face culling enabled ray, and the other one is front face culling enabled rays. By how they intersect with the faces, we determine whether we are outside the mesh or we are inside one of the tetrahedron and we are going towards another one, and we are exiting the face, exiting the volume. These correspond to case 1, 2, and 3. So rendering refinement tree traversal. So our aim in here is to, given a point, we find out which element we need to go, we need to traverse along the tree, and we need to calculate the ID and the vertices of that element. So for this, we need to identify the child elements. We use 3 tests for identifying the 8 child elements, children elements. First, we determine whether the sampling point is on the top left or right back of half of the current tetrahedron. Then second one is left, right, or top back halves. And the third one is the inner and outer parts. So in order to identify these elements, we try 2 techniques. The most simple one is the point plane orientation test. So for each half test, we require 2 orientation tests and 2 plane point orientation tests. And for the inner outer test, we need 4 inner outer point orientation tests, so 6 total orientation tests. And we also tried barycentric coordinate-based test. It simply uses the barycentric coordinates to do the same plane test. But since we know the barycentric coordinates, we can do this with simple arithmetic comparisons and additions, very simple ones. So this, however, requires 4 cross products for barycentric coordinates. We experimented on this too, and usually they are really close to in terms of performance. So one performance improvement we tried in for our rendering method is macro cells, coarse mesh macro cells. So macro cell is usually used in rendering to speed up the rendering. And a macro cell is a low resolution volume that's built over the volume data, and it stores the maximum densities inside each part of the volume. So what we do is traverse the volume, traverse the macro cells, and use this maximum densities to either in ray marching skip the macro cells, or for woodcock we homogenize the local volume so that it's more tight to the real volume. Generally, this data structured grid is used for that. But we said, what if we use the existing coarse mesh as a macro cell? Since we are already traversing the coarse mesh to identify the elements, so we tried this, and it also aligns with the theta-MR mesh better. And the second one is the view-dependent early tree traversal termination. So essentially, we stop the traversal when the element gets too small on the screen and sample that element instead of one of its child or leaf elements. So quickly going over the experiments. We use Tate code library for generating these volumes, and we synthesize some test data with different scenarios. We take, for example, heptane's data is from structured mesh, but Agulhas is unstructured mesh. So we changed some source of our data to make it generate some interesting various scenarios. And advection is we didn't synthesize that. It's a simulation. Advection simulation comes from an advection simulation. So if you look at the statistics of our data, they differ a lot, and usually average refinement levels are different. Their number of coarse elements are different, so they represent different cases. So if we look at the performance between our theta-MR rendering and unstructured base rendering, for ray marching, we are most of the time faster than the unstructured mesh render. Except for the advection data. This is because advection has small number of coarse elements and very deep refinement levels. Here, we waste time for tracing rays on the ray tracing course, and that's why it's a little bit slower. And for woodcock, similar story, but here Agulhas set is a little bit slower, and this is because for the other reason. So we are now wasting some time on tree traversals instead of using the hardware BVH. And for memory, when we look at the memory, we get maybe sometimes up to 2 times, a little bit more, 2 times compression. So our experiments, so for coarse macro cells, we have similar story like this. So everything is faster except for Agulhas set. This is because Agulhas have a lot of coarse meshes and are always trying to test for those coarse meshes whether that coarse mesh is empty or not. So it slows down and for woodcock, there is an interesting result. So for woodcock, for Agulhas set, it comes much more. Our coarse macro cell becomes too much slower. This is because we have a lot of trees, and for woodcock, if you have a lot of macro cells, you have to go back and each time restart the rendering. So this slows down the rendering time. So view-dependent early tree traversal termination, and we tried with some threshold values. As we increase the threshold, we terminate the trees from higher up, so less depth, and you can see we are speeding up the rendering, but we are losing some of the details. It is same for woodcock, but for woodcock we are getting less benefit from early tree traversal because woodcock takes less samples on average. So here's the plot of it, and when so we start with early termination of, uh, then when we enable it, we need to do some area calculation that slows down the performance, and as we increase it, we get some performance back. This is not possible with the unstructured mesh renderer because we don't have a refinement levels or hierarchy. So, and quickly conclusion. So we propose a direct volume render for the TTMR data, and we avoid explicitly constructing the unstructured mesh, and it achieves faster rendering times most of the time and reduce the GPU usage. And for future work, maybe extending our work with other AMR element types, and maybe some data parallel rendering can be used. Thank you for listening.
We focus so far. Is there at least one question? And then we go to the okay. Okay. So, let's move on to the thank you so much. Is for what systems with falls in this instruction one by in will let packages JavaScript of
Mhm. Hello, everyone. I'm Gautam. I'm here to present Walks to Serve, a faithful surface extraction from coarse binary voxels. So, intuitive tools for creating shapes using voxels have gained a lot of popularity in recent years. These tools allow users to place blocks in a regular 3D grid to create shapes, and this has allowed users without any 3D modeling experience to create complex shapes easily. And also games like Minecraft and building block systems like Lego are using this concept to build 3D structures. So our motivation comes from large quantities of the readily available data from various sources. But these voxel representations only provide abstract or low resolution approximation of shapes. They lack realism. They fail to meet typical modeling or rendering applications. So, how to convert these boxy looking meshes to regular smooth meshes without losing much details? So, reconstructing piecewise smooth geometry has been well explored in 2D. For instance, for instance in Polyfit, they vectorize low resolution images, raster images by perceptually fitting polygons. And in another work, an 8-bit art is processed using specific mask spring system to relax pixels to generate vectorized outputs. In 3D, the traditional methods like marching cubes and dual contouring, and there are several variants, typically assume surface to be smooth. Uh, they either uh, they either classify they either classify the corners of a cell using a lookup table or place a vertex based on a error function. They usually result in a uniformly blocky surface
with soft, not so sharp edges. While recent neural variants primarily focus on alternate representations, neural marching cube and neural dual contouring accepts binary voxels to be there in. They noticeably improve their respective prior art, but they still target higher resolution content, that is 128 cube or more, and they also still rely purely on local context. So their outputs often diverge from viewer expectations and produce unintended sharp features or suppress intended sharp ones. So we introduce walks to surf, a novel method to reconstruct feature preserving piecewise smooth smooth surfaces from binary voxel grids. Our method automatically converts voxels to voxels into piecewise smooth shapes while preserving viewer intended sharp features. But mathematically, all the edges of a voxel surface are sharp, but only a few appear to be sharp to the viewer. We address this challenge in three main steps. First is to predict the user intended sharp voxels using a deep learning based classifier. Then use these identified sharp voxels to create a sharp feature curve network, and later optimize the curve network and the proxy surface between the smooth curve network. In the learning step, we use a SwinUNetR based transformer network to create a coarse probability mask, um, followed by a custom made refinement module which focuses on local details. This outputs a 64 cube probability map. We chose SwinUNetR because it is useful in capturing um, long-range global 3D context, and the refinement module will focus on the focus on correcting local mistakes that may have been missed in the first stage. So in this way, the final prediction gets to keep global context from SwinUNetR and also becomes more accurate at local voxel level. So our learning step results in a heat map showing confidence of the prediction. We classify high confidence voxels as sharp. Now we need to convert this set of sharp voxels into coherent network of sharp feature curves. We do that by applying the linear triangulation on the sharp voxel centers and prune the longer edges. We can actually formulate this as a 2D reconstruction problem, representing each voxel center to be a vertex in 3D, uh, seeking a curve network. Since the curve network is made by connecting sharp voxel centers, we need to project it to its corresponding proxy surface. And we know that our voxel grid is a binary occupancy grid, which is 0 if it is empty, 1 if the surface is present. We create square faces adjacent to zeros and ones, aligning to the horizontal and vertical axis. And then we project the curve network extracted from the previous step onto this proxy surface by following set of rules. This results in a curve network in terms of mesh vertices. Now we smoothen this blocky curve network by using a mastering system. We place uniform masses at each of the vertices and consider each edge to be a spring. And we use a smaller rest length than the current edge length to and begin the simulation. As the simulation progresses, the tension forces tend to better align the vertices, creating a smoothing effect. And throughout the simulation process, we constrain the future extremities. Those are degree 1 and degree 3 vertices. This helps us to preserve the features. We also employ weak positional constraints, allowing vertices to not move more than a voxel diagonal length from its initial position. And also, in addition to this, we do a um, final inflation mechanism to prevent any over shrinkage of under constrained closed loops. This results in a smooth curve network which acts as a basis for mesh smoothing. Similar to the curve network simulation, we associate a mass spring system to the triangulated proxy mesh. This involves assigning um, uniform masses at vertices and considering edges as damp springs. We also use, similarly, we also use shorter edge lengths to, to start the simulation under tension. And the simulated curves corresponding positions on the mesh acts as the constraint, hard positional constraint, and we let the simulation begin under tension. This results in our final smooth mesh with user intended sharp features. Our method successfully reconstructs a wide variety of shapes from ABC dataset, and we also try to generate shapes. We also try to create shapes from organic shapes. Uh, they worked well, and we manually created voxel grids depicting few shapes and tried our method along with several alternatives. And we found that our method to be working fine, better than the rest. So to conclude, in this work, we tackled an underexplored problem of perceptually reconstructing surface from a coarse voxel sets. Our solution combines learning and geometry processing steps to um, best solve the problem and outperforms the potential alternate methods like NMC or NDC. So our learning step currently depend on ABC dataset. Improving sharp voxel detection could be an important direction in our future work so that we can handle more organic shapes. Since we do not explicitly check for self-intersections, our method might produce some, but generally do not produce some self-intersections. Yes, thank you.
Thank you. So nice. See, I think you showed one example where you showed some previous where you got this first backgrounds, and then you are this okay, this is okay. So here you got this backgrounds, and I was wondering if you could also extend this to 3D, so I can see that having only one
Yes, of course. It is fairly easy to extend. If you have a colored voxel mesh, we can, because at the end we are simulating or smoothing the voxel mesh, we can use the color, the corresponding color on the mesh. We could definitely try that. Yes. So our during our learning step, so, our learning step produces a probability mask, which tells us which voxel represents a sharp feature, which voxel, I mean, it's a probability of being the voxel being sharp or not. Manually take them. Yeah. No, no, no. The ABC dataset provides sharp features. So yeah, we train on ABC dataset. Yeah. I think it could be relevant, but initially we we thought um, how a result. I mean, the result is mainly how the user perceives it to be than the ground truth is. So in a medical application, the accuracy or the chamfer compared to ground truth has to be better than the voxel representation. So for us, how user depicts a voxel surface is our more primary aim. Yeah.
Hello, folks. I'm Jinesh from IIT Mandi, which is located in the foothills of the mighty Himalayas in the India. And before I begin, I would like to thank the organizers of the conference and the reviewers for their detailed and constructive feedback. This talk is about an algorithmic framework for subvolume computation. And here is the outline. So we'll first formulate the problem, then we will formulate the envelope condition, which is then used to first compute the wireframe of the output and then the faces of the output. And doing so requires a study of the change of the topology of the envelope with time. And then I will show some results. The problem of swept volume computation is a classic one in solid modeling. Yeah. So given a solid and a motion, the problem is to compute the shape swept by the solid as it moves along the motion. Yeah. And there are a number of applications of this problem. For example, in CNC machining verification, one may compute the swept volume of the tool, yeah, and subtract that from the block and compare the resulting shape with the desired shape. While designing gears, one may compute the swept volume of one of the gears along the relative motion between the two gears and subtract that swept volume from a block to obtain the shape of the second gear. Yeah. In collision detection, again, you have a pair of moving objects, and you could compute the swept volume of one of the objects, let's call it A, and along the relative motion between the two objects and check the intersection of the same with the second object to detect collisions. Yeah. Of course, now there are many applications, but the real motivation behind doing swept volumes is that it's pretty. Um, Now, this problem has been well studied. There have been decades of research in this area, and but when it comes to CAD applications, yeah, there are two main requirements. One is um, a high degree of numerical precision and a guarantee of topological completeness. And to the best of our knowledge, the previous works do not address these two requirements. Moreover, I am not aware of any general implementation of solid sweeps in any CAD modeling software. And in order to address the aforementioned issues, in our work, we resort to an algebraic modeling of the underlying constraints, yeah, which are then solved using subdivision-based solvers. These solvers, in turn, provide guarantees of numerical precision and topological completeness. Further, we have a boundary first computational approach, which leads to a robust algorithm. Right. Now, to get started in earnest, the input has two parts. The first is a solid, which will denote by H, and we use the industry standard boundary representation or BREP for its for representing H. Yeah. So in the BREP format, a solid is represented by its boundary, and this boundary may be composed of a number of faces which meet either with G1 or G1 or G2 continuity and so on. Yeah. Now, a face is obtained by trimming the underlying parametric surface by a sequence of co-edges. Yeah. So, for example, this magenta face is bound by 4 co-edges. Yeah. And in this work, we assume that all the faces, all the surfaces, and all the co-edges, they are all represented by B splines. Yeah. We also assume that any pair of surfaces can meet with G0 continuity. So which means there is a sharp edge wherever two faces meet. Okay. Now the second part of input is the motion M, which is denoted by M, and it's a one parameter family of rigid motions. So which means that for each time t in this sweep interval 0, 1, there is a 3 by 3 rotation matrix AT and a translation vector B of t in R3. So that under the influence of M, a point X is transformed as ATX plus BT. And we again use B splines in order to represent AT and BT. Now, given H and M, the swept volume H plus M is this infinite union of all the translates of H along M. Yeah. So this H of t denotes the translate of H at time t. Yeah. So by definition, the swept volume is a solid. And we again want to use the BREP format in order to represent the swept volume. So which means the problem essentially is to compute the boundary of the swept volume. Yeah. Yeah, the well-known envelope condition forms the basis of our method. Yeah, and this condition, this envelope condition, gives a necessary condition for a point to belong to the boundary of the swept volume. It says that as this solid H is moving along M, yeah, a point P on the boundary of H will belong to the boundary of the swept volume only if the velocity at P is tangent to solid at that point. Okay. Or in other words, the velocity is orthogonal to normal at that point. And this is exactly what is captured by this function f, which is defined on the UVT space. Here UV are the parameters of the surface H, of the surface S, which forms the boundary of H, and t is the time, there is a parameter of the motion. Yeah. So f of UVT is simply the dot product of normal at UVT and the velocity at UVT. Yeah. And so we are interested in the zero set of this function f. And that is this. Yeah. What we're interested in. And the set of points which satisfy this equation will be called the envelope set. Okay. And of course, at the starting at the ending time, at time t equal to 0 and t equal to 1, this equality becomes inequality. And that set is called the end caps. But this is the easy part, and we won't focus on this, but we'll focus on computing the envelope itself. Okay. So in the swept volume example shown earlier, this example, these are the two end caps. Yeah. And this is a envelope, which will denote by cal E. And like I said, this is the easy part because it comes from solid itself. So we will focus on constructing of the envelope. Yeah. In this work, we assume that the envelope is free of self-intersections. Okay. What that means is that the union of the end caps and the envelope is the boundary of the swept volume. So now we will focus on computing this envelope itself. So at a high level, our approach involves uh, computing this envelope by computing sections of this envelope at a few time instance and then fitting a surface through those curves. So section of an envelope of the envelope at any given time t will be called a curve of contact at t. It is simply the subset of the envelope for a fixed time t. Okay, and in the previous literature, this has been also referred to as a characteristic curve at t. So in this example, you can see the curves of contact at a few time instances. Yeah. And the envelope is by definition the union of all these curves of contact, E of t. So E of t is a curve of contact at t, and envelope is simply the union of all the curves of contact. Yeah. The output, yeah, has a natural VREP structure which is derived from that of the input. Okay. For instance, this magenta phase F here produce this magenta phase F sub E over here. This sharp edge, the colored gray, yeah, labeled E, it produced this phase E sub E over here, and so on. It's color coded. Okay. of course, a face may not generate anything on it. So this may be empty, okay? In some, for example, uh, this face did not generate, green face did not produce anything over here. So further, so we will use this sub E, yeah, we'll use this sub E in order to denote the geometric entity on the envelope which was generated by the corresponding entity on the solid. So F produced F sub E, this E produced E sub E, and so on. Okay. So further, if you have a coedge C which bounds this face F, then this coedge C will generate a set of coedges on the envelope which bound the faces F. Yeah. Now these coedges CE will not only bound faces FE but also faces E sub E, where E was coinciding with C. Okay. So for example, if you look at this edge over here, yeah, this edge, it bounds face FE as well as the face E sub E. Yeah. Now this faces E sub E, they are also bound by the coedges generated by the sharp vertices that bound this edge E. But let's not get into details right now. Right. So now the construction of the envelope begins with constructing first the wireframe of the envelope. And by wireframe, I mean the coedges, yeah, of the envelope. And so let again this C be a coedge which bounds a face F over here. Yeah, let this be the face F. Yeah. And let S be the underlying surface for F. So this coedge C is specified in the parameter space of S UV as C of R equal to U bar of R and V bar of R, P curve, you know. And in order to compute the coedges generated by this coedge C, yeah, that is, in order to compute C, we solve this system of three equations um, in four unknowns. Yeah. So your four unknowns are U, V, T, and R. Yeah. So the first equation says that okay, it satisfies the envelope condition. Yeah, that a normal orthogonal to the velocity, that one. Yeah. And these say that okay, it actually follows this coedge. Yeah. And all these three are precisely represented using B splines because all our input was in B spline, if you remember. And so you have three equations and four unknowns. So the solution in general is one dimensional. That is a set of curves. Yeah. And we solve this using subdivision based solvers due to Barton et al. And this solver returns a set of polylines. Yeah. That is a set of connected sequence of points. But the important thing is that this solver gives two kinds of guarantees. It gives a guarantee of numerical precision, which means that each point returned by a solver is guaranteed to be within the prescribed numeric tolerance of the actual point on the envelope. The second guarantee it gives is that of topological completeness. So it guarantees to return all the solutions within prescribed a subdivision tolerance. Yeah. And it is through this that our algorithm gives guarantees of, you know, topological correctness and numerical precision. So in this example, you see this magenta face is bound by four coedges, and they gave rise to these four coedges, which are shown in a color-coded manner in the UVT space and also in the XYZ space. Yeah. Right. So now we come to the wireframe of the faces which are generated by the sharp edge E. Yeah. So let's say this sharp edge E lies in the intersection of faces F1 and F2, and the coedges belonging to F1 and F2, which coincide with E, are C1 and C2. Okay. Moreover, E is bound by vertices V1 and V2. Yeah, these are sharp vertices. And like we said earlier, that the coedges generated by C1 and C2 will bound faces E sub E. Yeah. And that computation we already described in the previous slide. And so now, in order to compute the coedges generated by V1 and V2, we just use this. Yeah. So it's simply because it's sharp vertex. So it will trace a curve in R3. So that's what this is, albeit with appropriate trimming. Yeah. So for example, here, so C1, coedge C1, that is a coedge bound by yellow face, did not generate anything over here. The coedge bound by F2 gave rise to this and this portion. Vertex V1 produced this, vertex V2 produced this. Yeah. Okay. So now that the wireframe has been constructed, we proceed to computing the surface information. Yeah. And like I said earlier, that this is done by computing a few curves of contact and then fitting a surface through them. Yeah. So now we want to compute curves of contact at a few sample time instance. So for a given time instant t naught, uh, the curve of contact is simply computed by solving this equation, right? Where uv belong to this surface, underlying surface S. So we are again working with this magenta phase, right? Which is underlying surface SUV. And so FUV T naught equal to 0. So here you have one equation and two unknowns. So again, you have, in general, the solution is a set of curves. And again, we solve this by the subdivision based solver. And in this example, yeah, you see that a few curves of contact have been computed and they are shown by these magenta curves. So let's say you computed n for n different time instances, you computed n curves of contact, and on each curve of contact you obtained m points. So you have a rectangular grid of m by n points, which you use as a control point for fitting a B-spline surface, and which that surface is then trimmed by this wireframe, the coedges which we already computed, right? And we are done. If only life were a bed of roses, because it is not, such things happen. Yeah. See, the topology of the curve of contact may change with time. And so, which means you do not have a regular or rectangular grid of m cross n points. So you cannot just go ahead and fit a B-spline surface. And this needs to be addressed. And this is how we do it. So that portion where the topology changes is shown magnified over here. Yeah. In XYZ space. And the same is shown in the UVT space over here. And what is really happening is this, yeah. So at each time, the curve of contact has two components, but initially those curves go this way and later they go that way. So essentially you have a saddle point, yeah. And in order to handle such cases, we first need to locate such points where this topology changes. We call such points critical T points, and they are obtained by solving this set of equations: f equal to 0, fu equal to 0, and fv is equal to 0. The first equation says that, okay, this point belongs to the envelope. The last two equations say that the grad f, which is a normal to this surface in the UVT space, is parallel to the t direction. Yeah. And that's why this is happening. Yeah. So once you compute these critical T points, you get two kinds of points once you solve this. Yeah. In here, the envelope is hyperbolic at this critical T point. Here it is umbilic. Yeah. And these two cases are handled in a different manners, which means we need to classify the points as either hyperbolic or umbilic. And this is done by looking at, of course, looking at the Gaussian curvature of the envelope at this point. Yeah. And the sign of the Gaussian curvature will tell you whether it is hyperbolic or umbilic. And this function essentially computes the sign of the Gaussian curvature of the envelope. Yeah. And then you know what kind of point it is. And this is easily done. And so we won't discuss this. And in order to handle this, we simply split the envelope surface. Yeah. So so the C is the critical T point. Yeah. And this curve of contact at that point is shown in black. The other curves of contact are shown in blue and green. Yeah. So what we do is this is a schematic only. Yeah. So these are the co-edges in the red. So we split the co-edges at this point A, E, D, and B. And from this curve of contact shown in black, we obtain these four segments. Yeah. So these four curve segments along with these co-edges gives you four loops. And these four loops, they've bound the four faces into which the envelope is split. Yeah, so you get four faces. And in this example, those four faces are shown here in four different colors. Okay. So concept is quite simple. You just want to split the envelope along this curve of contact at critical T point. Now, these critical T points may also appear on co-edges, not only inside faces. So for example, here, you see, um, there's a critical T point on this co-edge, which bounds the envelope face. And you see, initially you have two components of the curve of contact, but later you have just one component of the curve of contact. And this is again handled by splitting the envelope surface across this curve. Yeah. How much time do I have? 5 more minutes? -2. So then, so the concept is similar that you just split the envelope surface. So I'm going to skip that. Yeah. And here's an example. And this only summarizes what I just said. So let us skip that and instead let us impolitely stare at some results. And so here the input has about 4 to 6 faces, and this took about 10 seconds to compute. Some more examples. And here is an example which has self-intersections, yeah. So which are not been resolved. So input has about 17 faces and 45 sharp edges, and the output has 250 faces. This took about 20 seconds to compute. Okay, so I'll just conclude now by saying that this work raises more questions than it answers. The list of things it cannot do is longer than the list it can do, right? But of course, I won't present the entire list in the interest of time, but only the most important ones. The first is the self intersections. Yeah, they have to be handled. Then degenerate examples. So there are, we assume that the curves of contact are actually curves, but there are examples where a curve of contact may degenerate into a surface, which is not handled here, and just things to be handled. So let me stop now here in the interest of time. Yeah. Thank you.
Thank you so much. Questions? Everybody? Sure.
Michael.
I don't know, certainly balance the there's reasons. I don't several point in that policy that facility one this the relations.
Yeah, so they are not identical, but they have the same sign. Yes. Yes, yes.
Thank you so much.
Thank you.
Şey var mı mouse?
Şunu
Eyvah.
koyuyorsunuz çift. O ileri geri yapıyorsun.
Tamam. Buradan şu spam onu buraya alıp her gün aklıma yazarsın. Yani. Adını gidelim işte. Bir tane deneyelim. Şunu.
Hatta şunu da deneyelim. Şey çıkartayım.
Tam tutuyorum.
Kendimi de ben de yapıyorum. Böyle başkasının çalınsa hangisini
Çıkasın. İyi, sabah. İyi ki. Hadi.
Şunu.
Evet, aklıma. Evet. Görünüyor mu?
Yok hocam şey sunum moduna geçince gözükecek.
And we can see it now. This is enough. Ah, okay, okay. Now, so, can you maximize your PowerPoint in the presentation? We got your presentation. Do you give consent about this recording? If you don't want, you not record this presentation. Can you hear me? Yeah, yeah. We can hear you. Definitely.
Thank you for that job. So hi everyone. I'm Xiao Xiao from Shanghai California University, and I'm very pleased to present our work published in the CAT journal. So this is the title, Professor Wang just mentioned it. First of all, about the background of this work. So the structures that we study are the spherical jointed structures. So they consist of cylindrical bars connected by bolts, usually arranged in specific patterns, and they're widely used in architecture, such like the lattice roofs or some mechanical parts, especially when additive manufacturing, and more recently the metal materials. So because of their excellent mechanical properties and lightweight characteristics. Okay. So the original motivation of our work was actually from the health monitoring of existing laboratories. Okay. So during the launch of this period of the structures, the geometries of the lattice roof may change slightly, but even small geometry changes will cause the node cap bearing capacity to change, and even to structural safety failure. So we would like to analyze the structural performance of these lattice roofs. But before that, we need an accurate CAD models. But usually, CAD models are often unavailable for early built lattice structures. Even when joints are available, the resulting CAD models usually only represent as-designed geometries, not the as-built or as-is conditions. So they will not reflect the current state of the structures in service. So under this background, we would like to reconstruct the CAD models directly from the point cloud data. There are quite a lot of point cloud reconstruction methods developed. So our goal is to find a way that can be robust, robustly reconstruct the CAD models of this particular lattice structures. Okay. So the first stage of our method is the plane fixing of the point clouds. So here I give you the 2D example for expression. So for this 2D plane sets, we would like to find a set of planes that best fits this plane set. So during the plane placement, we would like to find, for example, for this plane sets. So the three planes are the basic fit to this plane set. So during the plane fixing, we have two control parameters. So one is the approximation tolerance, and the other is the smaller size. And during the fixing process, the outliers will also be excluded. So the plane fixing should satisfy four requirements. First is the fidelity, meaning that planes should fit the points well. Right? So for example here, so the three planes here do not fit the point well. And the second is simplicity, meaning that actually we do not want a point sets to be approximated by one single plane, be split into several parts. So the third is completeness. That is for all the points that fall within the approximation tolerance that are all included in the fitting process. And the fourth is regularity. So we need to add some regularity constraints to the fitting process so that the orientations of the planes have a consistent constraints. Okay. So to satisfy all the four requirements, we formulate an energy function. So this energy function includes four terms. and each term corresponds to one requirement. So after minimizing this energy function, we are going to get plane region that balances the fidelity, density, completeness, and regularity. So next, I will briefly explain the four terms. The first term, the fidelity term, actually will measure the distances between the points and the fitting planes, normalized by the fitting tolerance. So if we have a smaller value of this term, so it means that the fitting quality is better. And for the simplicity term, we actually measure the ratio between the number of fitting planes and the upper bound. So the upper bound of the fitting planes can be estimated in that because each plane, we assume that each plane can only at least prescribe minimum number of planes. So this upper bound can be estimated. So let's complete this down. So we simply just calculate how many points not included fitting process. And like that. So actually, we would like, for example, for the cylindrical surfaces, we would like the planes fitted to this cylindrical surface to be parallel to a planar. So we add this additional constraint to this function. So this is the importance of the energy function. So after optimization, okay, we will get an optimized plane fitting in point counts. And the points are assigned to corresponding planes. So after we get the optimized planes, each point will be projected to the corresponding plane, and we can construct planar convex house according to the projected points. And this figure shows the planar configuration of the convex house. So for the initial planar configuration, you can see that actually the convex house overlap considerably. But after optimization, the convex house will have a better distribution. So afterwards, we will detect primitives and reconstruct the CAD models based on this convex house. So this how to optimize the plane fitting or how to get a better convex house. So actually we want to optimize or minimize energy function. So what we do is that we define 5 local geometric operators. So these 5 geometric operators are first the transfer operator, which actually to exchange the points belonging to neighboring planes. And we also have merge operator, which actually merge 2 planes into 1 plane. And split operator just splits 1 plane into 2. And exclude operator, which is to exclude points that lie far away from the fitted planes. And also with insert operator, which is to include the the outliers at the current state included in the fitting process. So these 5 operators will be iteratively applied to the energy function until the energy function converges to minimum. So you will see that after optimization, the convex house will actually represent planar configuration is much better distributed. So this is an animation of this optimization process. So in our implementation, we started the optimization for the initial planar configuration with the region drawing method. So actually, we initialize the planar configuration with the region drawing method, and starting from this initial planar configuration, we optimize the energy function to get the optimized planar configuration. So and we get convex house, the discrete convex house. we start the section that's on this convex house. So we first do this. So we first need to create the neighborhood relationships around this convex house. So how to do it? So for a given convex house, example here, for a given convex house, so its neighbor house are those that are closest to at least one of these vertices. So for each vertex, we can find a neighbor house. So to accelerate this process, we actually build an ADB tree containing all the edges of the house. So for each vertex of the house, we find the nearest edge belonging to another convex house, and this convex house is marked as a neighbor. And after all the vertices of the given convex house are considered, and then all the one-way neighbors of this house will be found. Convex house often as the neighborhood relationship around the convex house. So after this blueprint, for the segmentation of the convex house is based on included angle between the normal directions of two neighboring convex houses. If the angle is below a specified threshold, the two houses are considered to be in one group. So this segmentation of convex house is completed when every convex house is assigned to a group. So this shows the convex house segment result. So the middle figure is the convex house obtained after the optimization, okay? And then we can do this segmentation so that we can segment the convex house into different parts. For each group of the convex house, we need to identify whether it represents a cylinder or a sphere. So this actually becomes a quite easy problem. So we can actually use the principle of component analysis of the normals of the convex house. So the normals of a sphere, the principal component analysis would be three significant non-zero eigenvalues. So for cylinder, will be two eigenvalues. So this will help us to distinguish whether this group of convex house represents a sphere or a cylinder. After we classify the group of convex house as cylinder or sphere, we can approximate the geometric parameters of cylinders or spheres using the square splitting. So that is the headline of the entire reconstruction process. So in our implementation, before we generate the convex house or before we do the plane process, we actually have a pre-processing, which is to cluster a house. So that we can do the connectivity to each set of the points independently and in parallel. And this will significantly improve the efficiency of the reconstruction process. So this is the overview of this method. So let me show you some results. So the first example is the Voronoi lattice. So this lattice contains a intersecting blocks, spheres, and intersecting cylinders, okay, which is a bit challenging to distinguish the two spheres or the two cylinders. But our method is considered successfully reconstruct modern spheres and cylinders. We verify or test our method using the model from the same. And of course, the thing I can do the same doesn't provide the data structure and the point cloud directly. We actually discretize the models provided in the data sets to get the mesh and then to create the lattices ourselves, and then also to create the point data sets ourselves. And so this point data, it has varying complexity and also varying scales, and our method exists quite robust to reconstruct the lattice structures from this point cloud data. So we take the robustness and accuracy of our method. So since actually in real scan data, it is inevitably concludes the frame data with scattering errors, right, and measurement errors. So we have to verify that our method is robust to noise. So in our study, we get two different types of noise data. One is a random noise, and the other is outliers. So as can be seen from the results, so our method is robust to moderate noise levels, but for quite high noise intensity, our method may give some unrealistic reconstruction results. But actually, in real scan data, this noise intensity may not occur in real scan applications. With fixing, for example, the vision effect, which is widely used in point cloud segmentation, and also two different vectors, Passnet and HPNet, for this simple lattice units. But unfortunately, for this simple lattice units, the two different methods, the performance are quite poor. And for the efficient effect, it also gives incorrect segmentation for the overlap and BCC models, so which contains overlapping or intersecting spheres and more complicated connection with jewels and bars. Then we would further confirm our method with with the construction methods. For example, the point to cat, which is a deep learning method, and a variational method in fact. And to ensure a fair comparison, we actually provide same segmentation results to point to cat and index and to our methods. So here we only compare the reconstruction results. So after comparison, we find that our method is faster and also gives a more accurate reconstruction results than other two methods. And finally, we went from method to scan data. Okay. So what we did, we actually pre-printed lattices. So we have a model, and then we create a lattice, the cat model of the lattice, and then we print the lattice with a 3D printer. So this printed lattice, they have the surface defects because the printers were printed in material layer by layer, so the surface is not smooth. And then we scan the lattice with a handheld scanner to get the point cloud data. And this point cloud data will contain like the scanning errors, and also it may contain some data loss because for some parts of the lattice we may not get the points of the scanner. So this is two examples of the 3D printed lattice. So as we see that our method can robustly reconstruct the CAD models of the 3D printed lattice, and we compared CAD models that we constructed and the original CAD models. And actually, the error is actually at the same level as the scanning accuracy. So which also improves that our method is robust and accurate. Okay, so back to the conclusion. So we adapt the robust space-based algorithm to consider the fidelity, simplicity, completeness, and regularization of the thinking process. And we use the Spam comic styles as an intermediate representation to segment the point half efficiently. And our method is robust to moderate noise intensity and more efficient than other methods for reconstruction of lattice structures. So that's my presentation. Thank you for your attention.
Thank you.
So, so Shasha, um, one question, I saw like most of your data are actually synthesized from the traditional mesh, right? Uh, I'm not sure whether in real world application, do you have this kind of data that is purely just a sphere joined lattice? Do you have this kind of real world data?
And so actually the database like simply containing cylinders skills like Python and in Python engineering. So usually we latitude. So if you go to stadium or some sports center or see values, that kind of data is kind of latitudes. So they are typically consist of the spheres and cylinders. So in Python engineering, so if you want to get the CAD models of these structures, so we need to scan those rooms to get the data, the point data of the spheres and the cylinders.
Okay. Any questions from the audience? If not, let's thank the author of this paper for their presentation.
Thank you, thank you very much.
Thank you. Thank you very much.
For the problem.
So this paper is a structural analysis tags people uses for the analysis of the most process.
Yes. Yeah, I think it's okay. Okay, thanks, Mr. Chairman. I'm going to present this joint work with Italian colleagues. And here is my presentation outline. I'm going to start to recall some features of the paper and then talk about the context of assembly model. Then we will see the structure of this analysis we've conducted and talk about the geometric interfaces that we propose in this paper. That is going through the analysis of digital component catalogs and spatial distribution of interfaces, as well as the analysis of CAD assembly module operators. And I conclude. So some features of the paper and the relevance for several scientific topics that the component interfaces appear to be something that is efficient and multi-purpose entities for various applications related to the CAD environment. There are some formal definitions. That's a characteristic of the paper. There are many definitions in the paper, and that's what we've tried to really formalize as much as possible. And trying also to keep an eye on enlarging the range of interfaces and components that could be addressed
through the paper. The scaling issue is something important. And we've considered the context of commercial CAD software, their capabilities, and also the context of company-based CAD assembly model. So this is relevant for assembly modeling processes, among other topics, as it is listed here. So talking about the assembly models, the regular context is that you can find assembly models on repositories, okay? GrabCAD or Imati repository. And then you have either mesh assembly model or CAD-based or step files that are also frequently available. Assemblies from companies are hardly available. That's a strong issue, and that's why we set up this work. And interfaces between the components are some key information that can be used later on, as I already discussed. So what we've been doing is to focus on geometric issues about interfaces. Still talking about assembly models, as you can see with this example, here we have a cutout of a hydraulic pump and several local zones. You have component shape variability that you can face in assemblies, like here with the white zone that is here, indeed a bearing, a ball bearing, and the ball bearing here it's a cutout also, but can be represented with its balls or just with nothing as a simple solid. Okay, so you have a very wide range of representation of components that you can face. You have also a wide variability in terms of interfaces. It's not only surface contact, even though it's a fewer number, but you can have, if we consider this example, so it's the the dynamic seal of the pump here, and you have a Belleville washer that is indeed like a conic shape, and so the contact here is just a circular line. Okay, it's not a surface; it's a circular line in this case. So what you can face also is that still near the bearings here, so the brown areas that you can see here, around the elastic ring, you can see some distances, I would say, and the distances can be spread differently. And so that's also a type of question when you are handling these assemblies. And still about distances, for example, here with the nut stud configuration, you have this type of distance, 0.1 millimeter, but the question is that is it consistent or inconsistent? So how we could process that? So that's the type of question we find in handling assembly models. So the structure of the analysis we've performed is to say, because having access to industrial assemblies is very complicated, what we can do, since we know that on one side, of course, people in industry are using CAD assembly modules, okay, as you see here. Then we've been going through the fact that these CAD assembly modules have a set of operators, and we can structure these operators according to different sets. That's what we've been doing here. Okay, so the set of operators related to the relative location prescription of components, classically what the constraints that are specified to locate components with respect to each other. That's the L set. You have also another operator set that is related to the distribution of components, the spatial distribution of components, whether repetitive, linear constraints or rotational constraints like you have here for the screws. So that's a way to structure. So I'm going to talk about L and D operator sets. The other one I don't have enough time in the presentation to talk about. And so we have also component catalogs. Component catalogs is indeed what the industrial are going to use, because they are not trying to recreate components. Component providers are providing digital catalogs. And so we can start from that. And the digital catalogs, what we know is that the providers rely on standards in any case. Okay, so what we've been going through is to look at these digital component catalogs on one side, and also to look at the behavior of CAD assembly modules. And what we know is that because compared to repositories, in repositories, the model you find, you don't know whether the components respect some standards or not. You don't know whether the components and some standard what can be considered standard components are coming effectively from digital catalogs or not. Okay, so you have question marks here, and you don't know precisely what is somehow the quality of these models. Okay, so going through these inputs and analyzing these inputs is a way to get more information that can be considered as closer to what is the context of industrial people. So talking about geometric interfaces and how to define them, of course, we are going to, in the first step, distinguish what we've called principal faces. That's to say planar, cylindrical, conic, spherical, and toric surfaces, because they are related to the joints for most of them. And so they are directly connected to the interfaces we can face between components. That's one aspect. Then we consider, apart these principal faces, the secondary faces. You have you have an example here. So the primary face is a cylindrical one, but here the interaction or the interface between this plug screw and the casing here gives this type of volume, and here this freeform surface is indeed a secondary face. Okay, it's not a principal face as we have qualified it here. Then the interface, the definition is just the intersection between the component, but it's a non-regularized Boolean intersection. Okay, considering that as we can see, I mean, the intersection can lead to a surface, can lead to a volume, can lead to a curvilinear path, or to a point. Okay, as we have examples here. And so we have structured this interface to consider the fact that the interface can be decomposed into elementary interfaces. Elementary interfaces, that's to say, of one category, one manifold. So that's to say, we have a decomposition according to the fact that we can have volume elementary interfaces, that's to say, interference, as we have here. We can have surfaces, and surfaces can be with several partitions or non-path connected configuration. So that leads to different elementary interfaces. You can see here the two pink areas. if the elementary surfaces are connected, what makes a difference is the difference in terms of geometric parameters. Here we have an example with this tab washer that has a contact area here and a contact area here. So it's two planar contact, but not the same geometric parameters of the plane. And so it's two elementary interfaces. So yeah, you have also curvilinear and point. You have this example about curvilinear with the curvilinear contact between the ball here and the cylindrical part. And you have also point contact example between the sphere and the planar area here as an example, because it's an example of a simple cranking mechanism in a gearbox in this case. But you can have also more complex configuration of interfaces, like with gears, and in assembly models, you can find this complex distribution of interfaces that we are going to talk about a bit later on. So it can be also non-manifold, indeed. You can construct, even though it's not mechanically very relevant, but you could construct this type of geometric configuration where you have a planar contact here, this planar area, and you have linear contact here, another linear contact here, okay, that is connected to the planar one. So it's really a manifold configuration in this case, and you can have a punctual one also. Okay, so that's the explanation, but the definition that we give to the interface. And so one part of the study is the fact that we've evaluated and analyzed CAD commercial assembly modules to see into which level of accuracy this type of interface can be reached. And we come up with this value as a relative error level, okay, that is common to most of the modules. So that's a reference value. Then going to the analysis of digital component catalogs, what we can see that you have, even though you have large, standard definition of components, you can still have a large variability in terms of shape. So here it's from different providers, the same standard, but as you can see, I mean, the driving area or the screw here very significant weights. This is another standard. That's also a variability for the bearing. You have an example. What you can find also in digital component catalogs, the fact that for the tab washer, you never find the tab washer like that. You find the tab washer, I would say, in a rest configuration, because the tab washer, indeed, between the assembly phase and the working phase, is subjected to plastic deformation. Okay, and so the fact you have plastic deformation, of course, the shape is very different in the working phase and in the prior to the assembly phase. Okay. So that's what we can also highlight. But when we summarize some analysis of this digital component catalogs, what we find out is that indeed there is some invariant information, and the invariant information are the mounting requirements of a component. Okay, this is exemplified here with the screws, where the screws here, the plate P is really common to all the screws, independently of the manufacturer, the provider, independently of the standard, and so on. So this is really something that is a strong information, like the coaxiality with the thread for the other components, the nut part, say. Okay.
And that's the same for the bearings. Okay, indeed, I mean, for the bearings, the mounting requirement you see here with the cylindrical area of the inner ring and outer ring, and also the plates here that can be used for the mounting requirements. So that is also something that is common independently of the other representation. But there is a large diversity of components, in fact, and that's really also a challenge because you can find also some components in digital catalogs for metallic frames of windows and so on, like this type of component. And here the interface will be just a set of linear paths. Okay, so that also illustrates the wide diversity. Then talking about the special distribution of interfaces, what we came out with the CAD assembly modules is in fact the fact in CAD assembly modules you can prescribe the distribution in different ways. One way is to say when you have an angular configuration like this one, you can say n components and distributed over 2 pi, and the user either is saying prescribing the n components, and then the computer is going to evaluate the angle alpha, but it can be the other way also. And when people are doing the other way, sometimes they approximate, okay? And if they approximate this value as they want, okay, of course you have a round-off. So it can be considered and regarded as a minor approximation. But indeed, this minor approximation is going to have also an impact on the interface, okay, between the components. And so this is going to generate some noise in the model. And in the same way, what we can see also is that on the components themselves, this circular distribution can be also approximated. Okay, this is part of the modeling phase of the component. So these two approximation can interfere and add noise so that the symmetry properties are somehow lost. Okay, and so what is appearing as something important is that the symmetry properties of components and the symmetry properties about the distribution should stay to be consistent in the same accuracy level as the one that is used to compute the interfaces. Okay, and we see also that inside the website of some suppliers of components, the symmetry properties are not necessarily satisfied at this accuracy. Here you have an example for this supplier where you have effectively the two symmetry planes, but for this one there is only one symmetry plane found. Okay. So the accuracy is not the same the moment among the suppliers. To try to reduce these constraints about the symmetry issues, we've seen that when you have some configuration with gears, very often, as we've seen before, the wheels have teeth that are interpenetrating. So we get a large number of small interferences, I would say. Here, what we propose is to introduce the notion of interface envelope. Okay, so this interface envelope is in fact the domain that you see here in orange, and which we have properties here within this domain where the line of action that is appearing here is the basis of the meshing process between the wheels. the gear. And so this line of action contains theoretically all the contacts, okay, that can reduce to line of contacts in case of helical or straight gears. And if there are interferences, indeed, all these interferences will lie inside this envelope. Okay, so you can use this concept of envelope to relax the constraint about the accuracy as it appears here. And so this envelope concept can be also extended to thread depending on the representation we have here. Okay. So finally, what we can see is that we propose definition to characterize what we call a nominal assembly representation. We focus on the LND operator sets. We think that the epsilon tolerance that is linked to the Cardinal assembly modules is something important. And what we are trying to address is to go towards the notion of closed world assumption that is derived from the formal system of logic, where we try to identify configurations that we can characterize as true, that are effectively true. And this is sorry, this is illustrated with the notion of consistency of interface and enable, for example, in this configuration to characterize the fact that because the interference here is not based on the coaxiality of the cylinders that is within the tolerance of the modeler, this is an inconsistent interference. And this is also important, this notion of accuracy in connection with the tolerancing phase an assembly. You have an example here of this tolerancing configuration, where for tolerancing the dimension, the I here are derived from the components themselves, their intrinsic dimensions. The interfaces, as we've seen, are obtained from the LND operator sets, and the epsilon I here that are the purpose of the tolerancing phase are influenced by the interfaces I and G. And so it's important indeed to have the tolerance of computation of the interfaces much smaller than epsilon I. So why is, I mean, there is too much noise computing the tolerance if we want to use this type of information. So this is also reinforcing the fact that the interfaces must be computed within this tolerance epsilon. Then the conclusion, we've seen the main point here regarding the notion of strong impact of component interfaces, the mounting requirements that are appear as invariant, the notion of interface envelopes that can relax some constraints, and there is still room for some complementary work. Of course, thank you for your attention.
We probably have time for one or two questions. So the questions from the audience. Thank you for this very nice talk. So I know in the learning community they are trying to find out a nice way of defining CAD model that would be compatible with their with generative algorithm, like being able to produce valid CAD models using AI model. And I was wondering whether probably the answer is too early to know, but whether or not the analysis that you have pursued could be served as the basis of let's say parametric definition of a valid assembly that they could input in their generative structure to produce a valid CAD assembly, which is what they are not doing at this time. They can produce sometimes CAD models, but not at the same
Yes, it's a good question. I think that this notion of consistency and the aspect of accuracy we've came across show that it can be effectively of interest to try to use, I don't know how, but to try to use this type of input to get models that would be say ready to use, consistent, more consistent, of course. Yes, yes. Thank you.
Thank you. Any further questions from the audience? If not, let's take the speaker again. Okay, the third paper of this session was intersection detection algorithm of surfaces based on geometric features of spine curves.
Afternoon, everyone. My name is Aizen Wang. Welcome to my presentation on self-interception detection algorithm of sweep surface. In modern CDCM what follows, sweep surface play an important role in product design. Yet self-intersection analysis remains an open challenge. Into this issue, we present an approach for detecting self-interceptions in parametric sweep surface generated by a planar profile along a planar span. My presentation is composed of 6 parts. First, I provide some background on the topic. Next, we introduce the definition of sweep surface, local self-intersection detection, and global self-intersection detection of sweep surface. Finally, examples are given to verify the effectiveness of the algorithm, and we present some conclusions on the topic. Computer-aided geometric modeling method often generate self-interceptions when module shapes, like reference surface, sweep surface, offset surface. Such self-interceptions not only damage the model's quality, but can also lead to unpredictable failure in subsequent operations, like geometric processing or unsafe task generation. Therefore, the reliable detection of self-interceptions are critical capability modern CD systems with direct impact on machine verification and task planning. Importantly, exact sweep surface cannot make use existing numerous self-interception algorithms. Prior work has checked the special case, circular profile, type surface, and 2D closed profile generalized cylinder surface. No prior study has proposed an efficient method for self-interception detection in sweep surface, leaving a gap in CDCM workflows. To address these issues, we present a complete and accurate method for detecting self-interceptions in sweep surface generated by sweeping a planar profile along a planar path. We also classify self-interceptions into local and global types. For global self-interceptions, we further classify them into offset curve and offset stream cases. Mathematically, the parametric expression for sweep surface is defined by a planar profile curve and a spine curve as shown in equation 2, where the CFU is the spine curve. The CPV is the profile curve. RU is the rotation matrix dependent on the parameter U, thereby ensuring geometric orientation consistency. This figure shows the process of generating a sweep or surface based on a profile curve and a span curve. In figure A, the red curve represents the span, while the blue curve denotes the profile. The green arrow indicates the tangent vector at the starting point of the span. Figure B shows the sweep surface generated under these conditions. It further shows the sweep surface generated when the span and the profile do not intersect in this figure. Self-interception in sweep surface can be classified into two types: local self-interceptions and the global self-interceptions. Local self-interceptions arise when the offset distance from a pod on the profile curve exceeds the curved radius of the span curve, which is related to the span's local curve properties. The case 2 is global self-interceptions, result from spatial proximity between the two distinct segments of the span curve, leading to self-overlapping of the sweep surface in 3D space. This algorithm gives the detection process for local self-interception in sweep surface. It accurately identifies the presence of local self-interceptions. The detection of local self-interception in sweep surface is related to the curved properties of the span and the standard projection distance of the profile curve. This slide gives an example of a local self-intersection. By our algorithm, the local self-intersection point is detected on the sweep surface at the curvature extreme of the spectrum. This slide gives an example with two local self-intersections by our algorithm. Two local self-intersection points and are detected on the swept surface, one at each curvature extreme of the spectrum. Next, we present a detection algorithm for global self-intersection in sweep surface induced by single offset curves. The first detection framework integrates spectral curve analysis with critical offset distance computation. For global self-intersection detection based on offset stripe self-intersections, it can be classified into two types, as shown in the figure. The case one is minimum distance in induced self-intersection caused by local distance minimum along the parameter curve. See figure A. The case two is underpause introduced self-intersection caused by underpause effect. See figure B. This figure shows the geometric representation of global self-intersection in offset strips. The gray area indicates the self-intersection regions of swept offset strip. Based on above analysis, we present the main result of our work, the algorithm framework for self-intersection detection of sweep surface specifically. The algorithm shows remarkable effectiveness in addressing local self-intersections, global self-intersections introduced by single offset curve, and the global self-intersections caused by offset strip. From this algorithm, we can see the input is the one spectrum and one profile. The output is the self-intersection result. Next, we present some examples to show the effectiveness of the proposed algorithm in detecting self-intersections in sweep surface. In figure A, yellow points mark the curvature extreme of the spectrum. The red and cyan point mark the position corresponding to the maximum and minimum offset distance on the profile. Figure B shows the generated sweep surface. The proposed algorithm successfully detects local self-intersection regions on the sweep surface, marked by the red box in figure C. Figure D provides a section view of the surface, focusing only on the regions near the local self-intersections. As shown on the previous slide, the spectrum is a cubic nervous curve with the control ball matrix and node vector TS and US represented. The profile curve is a cubic B-spline curve whose control point matrix and node vector are DP and UP represented. This example shows a case of critical local self-intersection in a sweep surface. The spline curve has multiple curvature extra marked by the yellow part in figure A. But the local self-intersection is detected only at the first curvature extremal, as shown in figure B. The point corresponds to the minimum curvature value and the minimum offset distance. In this example, both the span curve and the profile curve are cubic nervous curves, as shown on the previous slide. For the control point matrix node vector, ds, us, dp, and vp. This example shows the robustness of our algorithm in handling critical global self-interception in Swift surface, which caused by the minimum distance of the span. Figure A shows the span in the profile curve, where the span curve has a pair of minimum distance points. Figure B, the green curve segment, the green curve represents the span offset curve with the maximum offset distance. Figure C presents the spectral result where tangential critical global self-interception point exists, which is also the only global self-interception point. As shown on the previous slide, the red span curve is a cubic nervous curve with a symmetric shape, whose control point matrix and node vector are ds and us. The blue profile curve is a cubic p-spline curve with control point matrix and node vector are dp, up. This example is present to show the global self-interception in Swift surface, which is caused by underport self-interception of offset curves. As shown in Figure A, the red span curve is a cubic B-spline. Figure B shows the green offset curve corresponding to the side point with the offset distance corresponding to the minimum projection distance on the profile. In Figure C, the red point marks a global self-interception. As shown on the previous slide, the red spline curve is a cubic B-spline whose control point matrix and node vector are ds and us. The blue profile curve is a cubic nervous curve whose control point matrix and node vector are dp and up. This example shows the self-interception of the offset strip caused by the minimum distance and the corresponding global self-interception of Swift surface, as shown in Figure A. The span curve is a cubic curve. Figure B shows the offset strip obtained by projecting the Swift surface on the xy plane. Further, we obtain the global self-interception point on the Swift surface by our method, the red point in Figure C. As shown on previous slide, the span curve is a cubic nervous curve whose control point matrix are ds and us. The profile curve whose control point matrix is dp. The profile curve is a cubic Baudelaire. This example shows the self-interception on the offset strip and the corresponding global self-interception Swift surface. As shown in Figure A, the span curve is a cubic number. Figure B shows the offset strip, and it can be observed that the offset strip has self-interception induced by interpoles. Further, our algorithm is applied to calculate the intersection between the profile and the profile curve and the subpatch of the Swift surface. The red point in Figure C marks a single global self-interception. As shown on the previous slide, the span curve is cubic nervous curve whose control point matrix and node vector are ds and us. The profile curve is quadratic ratio Baudelaire curve whose control point matrix is dp. This table provides a qualitative comparison highlighting the relative applicability, complexity, and limitations of the three approaches. This shows our method achieve greater generality and robustness. In the end, I give the conclusion of the presentation. We present an approach for detecting self-intersection in weak surface that address three types of self-intersections: local self-intersection, global self-intersection based on single offset, global self-intersection based on offset string. Also, our algorithm is mainly applied to planar specs. The purpose solution framework can be extended to the detection of sphere surface self-intersection for specs. In the future of this lab, we are taking tailored equation back and analyze the effect that all
It's your turn. Yes, sorry. Yeah, I can back to you.
Also, the consumption is explain this house is the normal way style. So in the motion evolution is more states the normal way of style. So like exposure strategy and style for kinder in the regular video back the English record the papa response second the sign and you go to the definition then you have your sign the profile to the tangent direction and in on the bottom we plan to have our finish yeah the same macro maybe we the speed from the step in the data in not on work on the for planar macro on the planar compact is most is mostly to be used in some and still the spot of the plan next changes you go and switch normal plane and then set profile of the get up against the use of the cell then seems this is how the profile is the spectrum the plane of the plane release spec in the mission is to the plane associated the profile the plane is the plane
the the manner and factor and the layer profile is is also the uh, what is the maximum degree of when the contracting QE? What is the maximum degree that you have tried for finding these issues? So one maximum degree that the degree can be the sensor already QE. But yeah, the degree is not a degree. Um, currently then down is right. The degree then yet still the degree is not back. And you know, but you can check the progress that as you increase the degree. Our progress is done. Sorry. We can we can compare our values with the other with the same by the result is that you think I have my count which is even even as paper on purpose to section it's dependent on yeah. If the number of that is equal to 7, then I need that's false about three operating stability of this one false.
Thank you for an introduction. And in the talk, we present new curvature bounded subdivision scheme. It improves over classic Cardinal-Clark subdivision, which I recall at the limit point has unbounded curvature. And moreover, the new scheme retains a quality of original quadratic attraction subdivision and does this with fewer pieces. So outline, as you see, we start with the classic stuff and move gently to the recent subdivision schemes. Cutler-Clark, it starts with any mesh. The faces can be multi-sided, no restrictions for position of irregular nodes. After first step, it is important for us, we get already quad mesh. A couple of more refinements, and visually we get like a smooth surface. What is important for us that actually already after one refinement of quad mesh, we get a structure so-called CNET. CNET black marks for the valence 5 in this example, and brown colored is for valence 3. And such input is already sufficient for high-end schemes. And if we add yet another layer of quads to the CNET, what is important, we can produce without any additional step, just by conversion from B-spline form to the Bezier form. One shown green Bezier, bicubic Bezier ring. It is important for us testing the quality of new schemes, since it is important. The scheme itself might be good, but even also it's important transition from the regular part to multi-sided. So we consider subdivision surfaces as a sequence of contracting bicubic rings. Here you see this extended CNET. We produce one bicubic ring as before. Still no subdivision. Cutler-Clark is very simple. One new rule is only for a central irregular point marked. Correct? I hope you see. So now again we apply conversion to the Bezier form. We get a new ring, and it is C2 connected to the initial. Since curvature of Cutler-Clark at the limit point is unbounded, it is known that it is known how to make it bounded. We have to find new rules not only for the central point, but also for its neighbors. Okay, we do somehow this and apply same conversion. However, it is really a naive approach, since new ring is even not C0 connected with the previous one. It is a it is a now correct interpretation of traditional curvature bounded schemes. There are many of them. We start with the CNET, but no, still no conversion to Bezier form. Now we have refinement, black marks regular refinement. You see red the new rules, and here I hope you see cyan marks the area for the next refinement step. And only now we convert to Bezier form. You see shown on the left one sector of this entire arrangement. And note that now we have 4 times more pieces than in Cutler-Clark case. And after next refinement, everything is okay. The rings are C2 connected. Now we turn to the new quadratic attractive subdivision. It was introduced also at SPM conference 3 years ago in Genova. And what is really new, it is already has two components. So-called black D-net, looks like something like a net before, but at the center you see what you call attractive quadratic. Refinement. We refine all control points where I hope you see there are 4 new red points. The rest are obtained by the standard refinement, regular refinement, and again, cyan marks the area for the next refinements. Similarly, as before, now we convert to Bezier form. Layout is the same as for traditional curvature bounded scheme. And if we proceed further, again, new ring is C2 connected to the previous one. And important point is how we start this subdivision. If you look back, you maybe get an impression that we take the extended CNet and just throw away the central node. No, it is not so in practice. In our approach, we really take only CNet, apply regular refinement, no special rules, only regular refinement. You see brown new nodes, and here to better see, get already this new for the to start our scheme initial DNet. And what is important that since these brown new nodes are obtained by the regular refinement, no special rules, the initial data is retained and the new ring will be C connected to the designers. Now, how quadratic comes into the game? It is really important but technical work. Now only very brief sketch. First, we take intermediate, the degree 5, so the guide of total degree 5. At the center, you see this quadrant. Later on, we switch from this intermediate guide to by degree 5, since it gives us more freedom, which is really important to get a high quality. And all calculations are done in symbolic form. In our case, we use Maple. And right now, also symbolic calculation. We sample this guide by degree 5 guide. Obtained data is transformed to B-spline form, and so we get this new B-spline control points. New rules for this that to the control nodes that we colored red. Quadratic, how we refine it? It is really very simple. It's just a shrinking. And what is important, it is somehow looks a bit weird, the structure from two pieces, but it gives us advantage that first it gives good, it is convenient structure for analyzing eigenspectrum of this subdivision scheme. Here you, this is a shown matrix. Here are new data is expressed via initial data. And what is important, since quadratic refinement lives on its own, there we have white matrix. What it means, it is zero submatrix. And it is gives convenient block structure. And from this quadratic part, we get what is expected by the theory, the dominant eigenvalue 1, then subdominant twofold, and what is important, the next eigenvalue is squared subdominant eigenvalue. What is needed for curvature to scheme be curvature bounded? Just we calculate eigenvalues of the matrix D, and due to this, since maximum it is less than lambda squared, we have already bounded curvature. So now finally go to the new scheme. Since nothing new we can say on quadratic part, it is here not shown, and shown only one sector what is going on with the DNet. Here mark what you do. Input is the same as for quadratic attractive subdivision uniform net. At some spots, we insert new nodes. Only at some spots. We obtain already non-uniform distribution of the nodes, and we are shown black. And for the magenta, we take the new rules. Then again, as before, conversion to Bezier form, and you see really spatial layout instead of 12 pieces in the one sector, we have only 5 pieces. And here comes another trick that brown circles mark the data that would be needed for next step. However, our input is uniform. So what we do, since we work not the global B-splines, but with the, how to say, B-spline jets, we transform this data to uniform form in such a way that we retain all second-order Hermite data. And so on. Now the question remains why we call it fast. Okay, so here you see 3 rings of the Kaplan-Clark subdivision. Here, first for the to recall, you see the structure. One sector has 12 pieces of quadratic attractive subdivision. New one, only 5 sector. Yes. Now we take 2 rings. I hope you see that it's really sparsely out. But if I would continue, the overall picture would be very messy. So what we do now here, we show this only rings without detail, just as like a collection of L shapes in each ring. And now we produce this in sorry. And now we produce these three rings. In case, careful, in, just a bit back. In case of quadratic subdivision, we have, you see, 36 pieces per sector. Our new RS scheme produces more than twice fewer pieces. When you look at this picture, I think you're still thinking why it is fast. Maybe this picture is really illustrates better. Now we leave class in peace and produce 4 more rings, overall 7 rings, with new scheme. And I hope you hardly see the tiny hole that remains at the center. And note, it is, I can't say it is slow, it is good, but there is a clear, you see, hole. And actually, with the same amount of pieces, we do what is actually suitable for the as a final surface. Now, concluding remarks, how at the final stage in production was done earlier. Now, nowadays, you see the principle is the same. No doubt we use the computers developing the schemes. So we have also the additional options like curvature shadings and so on. Now, on this quadratic part. As an example, you see a well-known monkey set configuration. On the left, in the middle, it is, as was already briefly sketched, we get DNet, and inside, quadratic part. When you see at the highlight lines the distribution, they are excellent. Now, what we do, we pull up the quadratic part and transform it to have a cup form. And final surface already with some clear bump in the original monkey saddle, but still highlight lines distribution is perfect. Is excellent. We play even more. We now take this cup and rotate. We get at the first glance really maybe crazy shape, but highlight the distribution again is excellent. And now we have to say romp even more. We do in the first 2 steps. At the bottom, the same as here, but we pull down this quadratic part and flip. In the next step, we pull it up and again flip to have the same form as in the as here. And what we produce, highlights are not shown, would be here in this slide, would be very messy, but you really see that we can really work, in some sense, control what is what this quadratic part. And so, already concluding, so I would say this new fast Istanbul subdivision scheme retains really a high quality of the original quadratic attractive subdivision. Let's call it Genova, since it was 3 years ago. And what is important, that the quality is retained, but as you shown, considerably less of pieces. And our scheme benefits from what was developed in the for quadratic attractive subdivision, and the real novel moments that we use non-uniform refinement of B-spline jets, and second, also novel, this, as I told briefly, localized interplay, uniform, non-uniform. That is the key of new subdivision scheme. So, thank you for attention. What? Yeah. It's the when we move and easy it's like all easy, right? Yes, it will like disappear or extremely small, but I haven't told our, how to say, we like, how to say, hybrid approach. It was in our earlier papers, but after some steps, we replace the whole with a really high quality finite cap. But why we have to look what becomes at the limit point, since it is at the limit point we have a bad quality. No doubt, this finite cap would also have bad quality. These matters are related. In case I correctly understood the question, we also prefer not this, how to say, entire subdivision, but as was asked, we concluded a high quality finite construction. But what is important is that anyway, to achieve high quality, a couple of rings of subdivision are needed. And the traditional schemes do not have a do not produce sufficient quality. And another point that subdivision surfaces, why we want to do sufficient amount of rings, they are very convenient for isogeometric analysis. Finite schemes also we have constructed G2 refinable, but they are considerably more complicated. That's the point.
Yeah. Oh no, I, I'm the postdoc from the USTC. Yeah. Yes. Yeah. Okay. Good afternoon, everyone. I'm Bing Li from University of Science and Technology of China. I'm very pleased to show our work split PhD. This is a joint work with Professor Zhou Wangyao. Blade PhD that is globally consistent modeling of blade surface using PhD splines. Blade surface in energy conversion system are not just ordinary free-form surface. Their geometric design is constrained at the same time by the aerodynamic performance, structural integrity, and manufacturability. As shown in the figure, the blade is divided into two main region groups. The suction and the pressure surface are the main functional surface. They govern the flow behavior and strongly influence the energy conversion performance. The leading and the trailing edges are transition zones between the suction and pressure surface where the leading edge is usually rounded to reduce the flow separation, and the trailing edge is called the smooth flow ejection. So the key point to design is the interface between agent regions must satisfy geometric continuity for the downstream engineering applications. The convention blade surface modeling pipeline is usually based on the trim nerves patches. Even this is widely used, but when describing the blade specific characterizations such as bending, twisting, and sweeping, this kind of tensor product parametric domain are topologically rigid. This rigidity often leads to the parametric and geometric discontinuity near the patch interface. While in practice, designers or engineers always rely on trimming, stitching, and other post-processing reconstructions. This will reduce the design to engineering efficiency. So in our framework, our design goal is to use one unified and also locally refinable representation to preserve this kind of course path consistency. In our framework, we use PhD splines, which provide linearly independent polynomial bases over hierarchical T-mesh. Its latest construction process associated with the interpolation formulations could increase resolution only where needed. This is important for our framework because we can reconstruct the surface from local geometric information to preserve the global consistency under unified continuity control. Here is the overall framework. The input is structured assembling of nervous patches. The output is a PhD surface together with the necessary error tolerance. The whole pipeline have 5 main steps. The first step is a boundary constraint unified parameterization to maintain the parametric consistency and structural integrity. Chord-wise and span-wise profiles are normalized throughout the root, middle span, and the tip section of the whole blade surface. This kind of normalization benefit to guarantee the exact corner matching and the boundary consistency. As a result, instead of treating each function regions as an isolated object, we give the whole plane a unified parametric organization. Then we should estimate local geometric information at T-mesh basis vertex, where for the interior basis vertex of each nervous patch, it can be computed directly or analytically. But for the boundary basis vertex, the analytical derivatives from any single patch cannot represent the cross-patch behavior. Therefore, we estimate by fitting a cubic curves along the formal unified parametric directions. Lastly, and is necessarily we set the mixed partial derivative terms to 0. This 0 is aimed to decouple the chord-wise continuity requirement from the span-wise swapping constraint. The results also show that this kind of estimation can give the final error cross boundary is well controlled. The next step is important because we want to build a place-specific hierarchical T-mesh. The key idea is to make the level 0 mesh more capture the place-specific characterized before the following adaptive refinement. Thus, this step wholly follows the section-driven blade design framework that is the very classic blade design workflow. Thus, we start from a tensor product within the formal unified parametric domain, and then this tensor product level 0 mesh is necessarily to constrained by performing some chord-wise subdivisions. This chord-wise subdivision is aimed to capture the root and tip bounding profiles along the chord-wise directions. Then the level 0 mesh also performing some span-wise subdivision to encoding the bending, twisting, and the swapping chapters of the blade surface across different span stations. Finally, the interface between different functional regions are further refined to avoid the numerical instability that could be caused by the interface's discontinuity from the input nervous patch. The following step is the adaptive refinement. Before each refinement, and we could classify the current active cells into 3 categories: boundary cells, interface cells, and general cells. More importantly, when we refinement the boundary cells and their associated interface cells are subdivided synchronously. This is aimed to preserve the boundary-wise parametric consistency around the different functional regions. Now, let's look at the validation examples. This slide compares the input blade with or without the span-wise variations. For the left blade without span-wise variation, its geometry is close to a roller swap. So span-wise subdivision in the level 0 mesh is not necessary. For the right blade with span-wise variation, there are several middle span stations to encode the corresponding bending, twisting, and sweeping characterization. So in that case, the level 0 mesh will apply several span-wise subdivisions to accommodate these intermediate span stations. Thus, our blade-specific level 0 mesh gave a consistent strap to preserve the mean aerodynamic shape. Our framework also supports the blade blend modeling. In engineering, a blended filter contour is usually introduced at the blade harp interface. This treatment is aimed to remove sharp corners and potential strings concentration, thereby improve the structural strength and the durability of the blade. So the blade filter model is assembled by stitching filter patches that corresponding to the blade surface patches. The same idea can also be extended to the village configuration, where a village can be treated as a span-wise extension of the wing patch, and the blended level 0 mesh will be designed to prevent such smooth aerodynamic transitions. On the other hand, for the globally consistent modeling, multiple hierarchical mesh can be stitched without any trimming operations. This boundary processing stage will perform the log synchronizations and coefficient blending on the overlapping intervals of the agent parametric domain, where the nodes insert on one mesh coincide between every boundary segments on the agent mesh. This kind of corner-to-corner mesh will achieve the whole J1 alignment across the shared interface. While in the current implementation, the coefficient at each extraordinary point are just a weighted average of their contribution. So its continuity is just ensure the positional continuity. This table summarize the corresponding quantitative result. Even for the multi-mesh examples, the main trait is that the error decreases rapidly across the hierarchical levels. Since our framework is started from a compact blade-specific level 0 mesh with a single refinement. Thus, our framework could geometrically reach target efficient and avoid the deeper levels even at the interface layers. This kind of overall computational efficiency comes primarily from the blade-specific design. This design align naturally with the section-driven workflow, which is the classified blade design flow. It controls root and the tip chord-wise profile. It characterizes the middle span, blending, twisting, and sweeping characterize. And it also preserves an efficient adaptive refinement pattern. So our framework is efficient, not because it refines less, but because it refinement in a structure-aware way and maintains a consistent cross-bound control. Lastly, I want to classify the scope of our contribution. The motivation of our framework lie not in the PAT's plan alone, but in a blade-specific pipeline for surface reconstructions from trimmed nerve assemblies. During the whole 5 main steps, some steps are pretty special, such as localized geometric information, but some other steps have broader principles and can be generalized to other locally refinable spline representations. Therefore, our framework could be viewed as a blade-specific implementation of the spline over T-mesh, not just the PHT. And to conclude, we have proposed PHT. We have proposed blade PHT, which is a framework convert multiple trim nervous patch into a unified PHT surface that without any trimming operations. And the whole resulting surface can capture the key blade features with high geometric fidelity and provide the verified continuity across the interface. But future work also have something to do. First is to do some related works about the interior extraordinate vortex. The most important we want to do is downstream applications such as further integration of analysis and manufacturing constraints. Thank you for your attention. Thank you. Yeah, yeah.
Flowing of the within this G1 continuity, maybe this representation that's going to be
Oh. No, we have not do some analysis in implement, but what we do now is just try to a new framework. This framework is blade specific, and we want firstly to do some download such as manufacturing work, but not the analysis work. And the G1 should be improved future, but now is just G1. Fine. Uh, yeah. Yeah. Yes, we want to do some related manufacturing tests, but we have not yet to do this. But also we have seen a lot of already implemented examples. They already exist that questions, But I thought our pipeline won't get the high geometrical continuity will solve this problem. Thank you for your question.
Can you help me? Well, I don't know. The flores. So can you put which one? The PDF. Okay. Okay, thank you very much for the introduction. And thanks to the organizers for the excellent work up to now, at least. We'll see. So my talk today is about a scheme to generate smooth surfaces, smooth meaning G1. Okay, and it will have three parts: a short introduction, the derivation of my new G1 masks to generate these G1 surfaces, and some experimentation. So, getting right ahead to the introduction, as you might know, this is a very classical topic and very well studied by many people and by many distinguished people that are in the audience. So, just to mention a few things, the method of Bonneau and Hartmann of the G1 biquadratic four splits. We heard already before some talks from Karseuskas for the quadratic attraction and the Gaudian subdivision things. There's a lot of works in the area of arithmetric analysis where G1 surfaces are also important because we need continuous derivatives along globally on a surface or globally on a domain. And all of these different approaches, well, they have different constructions. There is a variety, there is a zoo of different constructions that you can consider. Recently, we considered a specific construction for the Catmull-Clark scheme, a way to have local masks that generate globally G1 surfaces that agree, that are bicubic, and they are the same as the Catmull-Clark scheme in the regular part and very close to them in the irregular regions. And of course, there is polyhedral net splines by Jörg Peters and Kauskas, and the celebrated papers, the constructions that use low degree surfaces. They have mixed topology. They can do quads or triangles and so on. And they also minimize the curvature close to the EV. So we are also working in the same direction. And I want to start with a with a two-sub subdivision scheme that you might have heard of. So it's a dual scheme. It produces biquadratic B-splines at the regular parts. And every time you subdivide, well, after the first subdivision, you have the property that all the valences of the vertices is 4. We saw this. We saw that also in the previous talk. And you have the fact that for every vertex, you generate a new face after the subdivision. For every face, you keep the face and you shrink it a bit. And for every edge, you generate again a new face, right? You see? So, and when you do it again, you have the same thing, like the faces shrink, the edges generate new faces, and the vertices generate even new faces again. So if you do this up to infinity, you get a smooth surface. It is a stationary scheme, means that you always use the same simple rule to subdivide. It's a dual scheme because of this fact, because every time you generate, well, vertices become faces and so on. And globally, it is G1. And well, there are several variations. The classical scheme is G1 for low valences at DV, up to 8 or 9. And the point is, the problem that we want to treat is that there is no final parametrization at the vicinity of these irregular faces. So regular faces have are quads, irregular faces are polygonal faces of different valence. Okay. What we want to do is to directly, instead of doing subdivision, directly produce a Bezier spline, which is G1, and gives you back a surface which is globally G1. Okay. And to do this, first we should define our Bezier representation, like here, the SUV. These are Bezier polynomials, and you will get one by quadratic Bezier polynomial for every regular mesh point. So you see that in this case here, we are in the regular case. Why? Because we have a grid. It's a 3 by 3 grid. It means we can directly interpret this 3 by 3 mesh as quadratic C1 splines. And we can directly produce masks, which are just not insertion, and will produce our Bezier surface. If you are close to the irregular vertex, then you see here that the grid is not anymore a regular grid. It has here an irregular part, and that's what we are interested in. Okay, we can try to apply the same averaging masks, but in that case, we will get a nice surface like here and here. But if you look closely, you will see that it will not be a G1 surface, because close to these irregular parts, the quadratics are not enough to get G1. Okay, so in this talk, I want to derive some new G1 masks that will fix this problem and will produce always a G1 surface. And yes, so I showed you this point where you don't have the right continuity, and that's what I aim at, and this is going to be the G1 ADS scheme. What are the advantages of the new scheme? So we will get explicit Bezier points with local symmetric masks. We will use higher degree RTVs, biquartic at odd valences and biquintic at even valences. It's a robust scheme in the sense that we do get G1 surfaces up to machine precision, and we get a minimal number of patches, actually one patch per vertex of the initial mesh. All Bezier control points that are on the corners are interpolatory at the limit do sub in surface, and we get a globally consistent normal field and good curvature. Okay, so to start with it, let me just recall tangent plane continuity on a common edge. You have C0 accordance, and then you have this relaxed G1 condition that says that the derivatives on the two sides lie on the same plane. They're not the same, but they lie on the same plane. And here, when you write this, what you have to actually define is what we say gluing data, or people say the transformation between the two patches. These are these two functions that actually control what is the transition of the normal from the one patch to the other patch. Yes, as Jörg was telling me, show me your transformation, and then I know what you're doing. So it's that for him here, I guess. And then when you have, so we start with this, and what do? We plug in Bezier coefficients, so we get this kind of conditions, okay? And then here comes the next thing. What we now need to do is, instead of using the Bezier coefficients, we are going to move into the masks. Here was the masks, so we convert the Bezier coefficients to a local mask applied to the ring of coefficients which I showed you here before. So R is the ring of coefficients, the ring of mesh points, and Q are these masks, some weights that I'm going to use in order to compute my local Bezier point. So if you do that, then these relations translate to relations between the masks, between these vectors of weights. And that's what I do here. So after a small, so to say, some algebraic manipulations, I can write down all these conditions, which come exactly by doing equality, well, translating this equality into linear constraints. And what I can do, I can triangulate the system. How do I triangulate it? Actually, I will consider some masks, the ones which are not marked here, from the existing scheme that I showed you, which was just a plain do-Sabin scheme, well, Bezier extraction on the do-Sabin surface. And then I will try using this triangulated system to recover a consistent solution for all the other points. And I will go order by order. The B0, I know it already because I told you I wanted to have it interpolatory on the do-Sabin surface, so I know the mask for that. So I go to first order masks, and this will be the point M01 and M10 if they are symmetric. As soon as I have a solution for them, I will go to the next equation, and since my system is triangulated, this next equation depends only on the masks that I already computed, and I continue this way until I find a full solution. Huh? I just want to give you the intuition. But if you do this in a systematic way, and if you study all the matrices that appear in the process, you can show some things like the fact that the matrix that appears here sees a circular matrix because you change the conditions for the G1 on the edge all around. And so you obtain a circular matrix, and you can prove that this matrix is symmetric, singular, and it has a kernel that you can actually have it explicit. So we prove that the kernel of this matrix has some sinus and cosinus terms inside. And then you can also prove that this matrix, I plus C, well, identity plus this circular block circular matrix, is actually invertible, and you can solve the system. So we do this kind of manipulations, and we continue in a triangulated form, and we find a general solution. And in the process, we also, we assign specific solutions to the problem. Okay. So if we do that, that's what we get for valence 3. We get this kind of masks. You can notice already that there are some negative points, negative weights. So it's not a convex mask. It is a partition of unity, but it's not a convex partition of unity. Well, as a side note, we tested several things. This does not affect much from our construction. And that's what you have. You have these masks for these points up to order 3. And when you do that on a mesh, here you have the patch structure, you have the original mesh points. Then using these masks, you generate degree 4 nets that fill this hole. Okay. Then we can do the same for the even valence. The construction is a bit different because always there is this split between even and odd. But the idea is the same. We triangulate the system, we look at the matrices that appear, and we go order by order to generate new points that recover G1 continuity at all edges. All the points that are not marked are, so to say, are classical, well, do-Sabin points, do-Sabin Bezier points, degree elevated to degree 5. So we do these tricks like degree elevation on knot insertion in order to arrive to the space that we want to use every time. Okay, and this is how it would look like for valence 6. You see that the weights are explicit actually. You can see the partition of unity. And you see, okay, actually this is the typical mask. But for the first order and the second order, these are some new masks that we generate, and you see that they are locally around the ring of the irregular face. Okay. And so we take these masks, we apply them, and that's what we get. Again, when you are around this kind of configuration of a patch of valence 6 on a face of valence 6, you have the underlying patch structure, and we're going to generate one patch per vertex, and all these patches outside, they are quadratic. And the patches inside will have degree 5. Will have degree 5, and they will meet with G1 continuity. Right. This was the construction, and then I will finish with my last part, which is some experiments. We did some surface interrogation. First of all, we check the jump of the normal across the edges or the interfaces, as well as the Gauss curvature and the mean curvature. Of course, we don't have curvature continuous surfaces, but we just want to check if they are if the jumps are small or if the value of the curvature is bounded. And of course, qualitative metrics or measures like the zebra lines to see the smoothness around the interfaces, and curvature maps to see how if the curvature is big and it jumps or not. Okay, so first a few numeric results. We tried it on several benchmarks, surfaces, and we actually compared with polyhedral net splines, which also contains an open source implementation, and we were also aiming to. We also made an open source implementation, and I think that's really important that people have open source implementations, then other people can use it, can compare it. So that's very good. And you can see, if you remember this polyhedral net splines, it also optimizes for curvature. We don't do that. Our construction is a bit different. What we do is we optimize for really accurate normal up to machine precision, and that's what we get. The jump in the normal is always at machine precision. And the curvature, it depends. There are examples where the curvature is better in the one case or in the other case. You can also check the zebra lines, and you see in both cases these are G1 constructions, and then it's kind of aesthetic which one you prefer or which one you think is better. The polyhedral splines have a better ISO lines in the coarser meshes. Then after, when you go to finer meshes, both in this example, both methods are similar, but this is a pattern that we kind of saw. Another thing we tried is to check, well, we knew it, but we checked numerically that we stay close to the do-Sabin limit surface. Why? Because we would like to provide to the designer a tool that is predictable, meaning if the designer used to work with do-Sabin surface and design the surface in that context, when we tell them, okay, now you don't need to do many subdivision steps, but you can just do one Bezier extraction step and get the surface, it should be almost the same surface. And we figure out that we have quadratic convergence to the do-Sabin surface and under subdivision, and also the normal converges linearly to the do-Sabin limit. Okay. And then some more experiments with larger benchmarks. Here we report the number of irregular faces, the valence of these faces, number of patches. So because of these local masks, this is massively parallel. You can do it independently for very big meshes. These are some meshes with a few thousands of patches. And for these ones, yes, we get easily the G1 result. Here's the patch structure, and here is some zoom in at some EVs of the final patches. Some of those were a bit nasty because they have singularities at you have these kink points, but this doesn't matter for our approach. We still get a good result. And so to conclude, I showed you a method to get G1 continuous surfaces from polygonal meshes with arbitrary topology. It produces a minimal number of patches. It's explicit, symmetric. The masks are symmetric and locally supported. And you can pre-compute the masks and you can make it massively parallel. We submitted this to the reproducibility stamp, but we were a bit late, so it's not out yet. each other review, but we don't doubt that it will be available for you all. One future work that we want to do is to apply all these results as geometric analysis. So with this, I would like to thank you for your attention.
Using P7 is the advantage of experiences that will and then the picture as
Yeah, yeah, they have to be split. We always apply one, yes. Yeah, yeah, yeah. But it's of course it is an interesting problem to allow for close surface.
Yeah, fish are not yeah, going so in case in classification the problem
No, no, the solution is explicit. This derivation is theoretical. We prove that this matrix is always invertible, means we can invert it and always obtain the solution for the first order. It's theoretical. There's never a problem in inverting this. Of what? Ah, yeah, yeah, yeah. Actually, the whole construction does not depend. Only depends on the topology, but not on the specific values. The mask only depends on the topology of the mesh, and the weights they don't depend on the specific mesh.
asking the same question that I asked the because guys 2 weeks ago. Why we are also waiting to stop working on this? And the one in this we are already trying to incorporate because stuff finding surface is why by all one is so we have this evaluation condition once in one time it's such more living in one humans or maybe a station it's easier as most you want to try. My question was would it be useful to have this integration concept or what would it be
Which points?
this
Ah, hmm. This would be yes. I've never tried it, but it would be like we would wipe this out and we'd start again because you see the first thing I said somewhere here. Mesh nodes are interpreted as quadratic C1 B-splines, so they are not interpolatory here. Yeah, I didn't know that this is interesting. Maybe you can do it, but I don't know because we have to also start from the beginning. Okay, thank you very much.
Başkan, just başkan.
There's someone. And then yes. Thank you. So I'm trying to give you an overview instead of uh, of, of this particular paper. And then the title, you see it, there's a strange word called it's common in the chemicals, like structures. And then, so if you notice also the mic, it's spiritual. I created on the three structures. And then the first one, I will give you an overview of conceptual shape algebra approach. Actually, the reason I'm thinking this is very exciting research direction. And then you can see it here. There is this is really to me a treasure. Like you can find so the whole idea is go to higher dimension and then look at different design structures. And then if you ask me, then I created the first one with the AI, and then I changed all the faces of all the cartoons. So let me give you the example here. When we say, we usually say non-manifold. Non-manifold is not like it's what are the non-manifold? There are differences between them. I have one. I found it. I don't found that. So this thing done actually the 2 days ago. And then this is a good way of like look at the structure. You want to do some structure like this. You can play with it. It's not just well, it's like the but how you can model it? So this is the one example of the one manifold in this. It may not be manifold one with maybe like one. The first one is like two manifold. We are so obsessed with the two manifold and three manifold. Actually, I work on the two manifold, three manifolds also. Like this looks like a very nice idea, but even the non-manifold is interesting. So this is an example. Another interesting idea. I'm for a long time, at least 15 years now, but I never said it openly. It's like some kind of the replacement systems. Just think about replacement system in the sense that I have a scaffold. I create makes sense. You can do whatever you want. It is your idea. So the one is the design choice. It may be interesting. And then if you figure out, you can find infinitely many of similar things. So I'm great. I'm like, we create something very exciting. I don't know. And it looks like, oh, this is the only one created. Actually, it is not. There is many. So when I was my student, I was thinking, actually, oh, I was thinking that way. So I was always thinking about some of that. So, for instance, in 1990, I wrote a paper which I called the generalized function. Actually, I generalized Minkowski distance, and then this can be created very easily. Just think about you have a symmetric linear functions, and then you take their intersections, and then they generalized Minkowski distance. This is generalized starships. So in this case, you get the half spaces, and then all the half spaces want to form the same one. And if you take the union and intersection of all intersection, you get all the possible star structures. And then those stars are something over there and look, it's done. Actually, that was I the present records in that when I was a PhD student, I created the records in the cartoon by using the same method. I used to put as well because in Turkey it would be interesting. But anyway, so for some reason I'm not. So later on, I created this kind of generalized algebra, and then I can create like almost you can say but in my second talk, almost like a statistics function. This is the 1999. In this time, subdivision surfaces came. There was just clear that subdivision and these surfaces may not be a big deal. So I'm surfaces what it is. But this is the example of what we created in the box. This is still I did in the confirmation action function paper that will run the whole thing. So basically what we came up this, we can create any two-manifold mesh, oriented two-manifold mesh, by using only four operation. This is like a risk kind of a structure. Create vertex, new vertex, insert edge, delete edge. We can create all of them. The beautiful thing, you are not bounded by the triangles. Okay? So I was going against to study in some sense because everybody was doing the triangles, and then I was saying, okay, don't worry about the triangles, do whatever you want. But the advantage is you have an incredibly big design space. You never had this kind of design space with the triangle. Your bounded with the triangles. What is the price you pay? If you do the triangle, nobody does this. What is the problem? Vertex. Vertex is extremely complicated. Actually, when we learned the first paper, it is sure not. And then they were getting the holes around the vertices, nobody can see it. Same problem happened in the three manifolds. You never know what kind of like that maybe even donut exists in the around the vertex. You never know. Everything looks good. Maybe it is not. So in order to do that, you need to create some kind of plot. So this is one idea. When you do it this way, suddenly everything becomes extremely easy. And as you imagine, I didn't have a PhD program at that time. But I didn't have some of the students in my home. Those students built this, and then they ended up at top mod. Top mod become extremely successful. The people use it. It's not interesting, yes. Last one. And then I was meeting with my PhD student, I think the students, and then I got the email from a New York designer, and then he moved the top mod to the web by using cloud. And then some of the stuff doesn't work, but probably you could hear it, and then we will be able to get the non-oriented services, etc. But the university became very excited, and then in 2008, they wanted to make the top mod commercial. Of course, as I told you, I made the commercial now. But they killed the top mod. But at the same time, they wanted to non-oriented services. Actually, this is one thing. Not one thing. All thing we need created to this operator. This operator. Oriented services. When you non-oriented services, you have a very well-defined structure. You can turn them into model structures like this. But the important thing, all model structures are not like what most people crazy ideas. When I say crazy, I have a pentagon here, it's kind of the operation. It's not like that. The only twist the edges. Why do you think that? Because in the two manifold, if you send the two sides, when you twist the edges, two side twist, and then it's squeezed level 2. And then you can get the large number of like a plane weaving, like cable weaving, etc. Like what was several paper on that. Then it's like this way. Then someone asked me that, I don't know, a few days ago, when you write the paper together, draw them. Actually, this paper I've done drawings. Actually, my one collaborator, gross mathematician journalism, don't completely call this figure. Why mistake? It got the line citation. So, it's 2015 paper, not there. Oh, I saw it. Oh, many three manifolds can be created, but it is so general, it is completely useless. This is mathematics paper. I like mathematics paper, but it is like whatever. So I went with Vinesh, you can see his name. He's a mechanical engineer. He's like me, crazy, okay? Like really crazy. Sometimes I feel I'm not crazy enough. Raman will be there. Like we push each other. Like my previous collaborator, Arnold, was in general always feeling like I'm crazy. Like he's crazy. I'm not going to shoot. I have to control him. He says, let's not crazy. Completely crazy. No, it's not like that. Not general. I'm not. But what we discovered? We discovered so many things. We didn't understand. These are the three honeycombs. He generalized three honeycombs. He didn't even understand what because he came to me, he said that no, there is like this. You can look at the videos, etc. I don't want to show you videos and spend time. So we come up with different methodologies. Those three honeycombs are different than this honeycombs. They are different than this honeycombs. They are different than this honeycombs. And then their mechanical properties are different, etc. Most important than this plot took. Actually, I didn't present it. This was a Kennedy figure. Actually, last year I was supposed to present it in China. I couldn't go to China. I didn't present it. Like it was in the Kennedy. This guy is like the 16 structures. They have holes, but you can put them together. You can disassemble it. They don't become cheap. That's the reason I call it the I'm not going to place a headroom on cheap. So we took all this kind of stuff, and then if you look at the information over there, if you went and look at the Wikipedia said that no, nothing beyond the text structure are well known. You cannot imagine. Like, and then you write these papers for, I don't know, 6, 7 years. Like, you have someone lost here, lost here in this opportunity. So in our Nexus, what we come up with some kind of system again. We get this, like a, just think about the like a host structure inside of it. We mirror them, and then we are able to get that very strange stuff. I will show you this. Claim weaving is the weaving like this. Most of you are wearing the claim weaving, and then my previous paper was the claim weaving was done that way. It's the exactly the same. If you do it in the volume, it's different than look at that. There is only something in 2D. However, in the 3D, you need plane waves. I'm not talking about all possibilities. All the plane waves are exponential increases. There's a huge design space exists, which means like what does it versus open? Where's open? Okay, talk about okay. Talk about the some versus other couples also like this initiative of that one. I didn't like that because and then we talk with some people like because we need these things can be done can be used very composites. We need those like we come up with some of the design stuff. Like this is the RSMI paper 2 years ago. I want to this is the RSMI paper last week. So this for the crazy graphs, they go into each other. It's very structured. This one are the links we can run the structure. Now this year, we wanted to do something crazy. Makes sense? Because the links, mathematician knows about it. Mathematician knows about us. But there's nothing more concatenate. Not defined my language so concatenates are something like this. You have some graphs in 3D. You put them and then repeat them. They become interesting. This is terrible because when you do it, I have no idea what they do. Like what I mean. What kind of structure? What is design prompt? So crazy creative. I don't like creativity. It doesn't mean that I like creativity. But I don't like creativity in the mathematical design space. Okay? Because I didn't generalize. Then I noticed this. This guy is not creative. If you look at the lots of papers, I don't know. And 20 paper about this structure. This structure is a then I look at this structure. It's a primary structure. Look at that. There is a like you can think about some cubicle space, and then it's cubicle. That's another cubicle space. They draw all the cubes. You got that? Once you understand, yes. Once you understand that everything comes, all you do, create some kind of private honeycomb, because we know how to create honeycomb. They do them together. Oh, you get them. So we suddenly increase the wall space. So think about it. We can ignore it. Offer it that when coming from the oxygen doing stuff. What is it doing? You can put different things in each wall. So what we can do, instead of using the wall of that, actually I will show you the whole there. No, it is so complicated. Okay, here. So this is prime of it. So in this example of big shots, this is very well like famous shots. We first identify what are the dual. And then it's two. Dual and themselves are the same. The important thing is which one was the only one they did exactly the same. This is hexagonal prism, still I guess that each one of them is different. When you think about that, and you can get to this component creating sets. How you can create that? Just think about this structure. You beat them, you fill the space. But it's very structured. Then I will talk about our experience with the old stuff. We don't have to use all of them. That was our several experience. Also, like instead of putting all of them exactly the same, we can do different ones. What does it mean? Now, instead of repeating those things, I want to make a strange repeating structure. I can repeat it. That makes sense. So, actually, that's the position. That's the logical paper. Actually, that's the abstract paper. So, there's something called fundamental domain. Fundamental domain is basically what domain is the smallest thing. Actually, I change the word. I use periodic domain because just about periodicity. If you have a periodicity, like some kind of sine wave, and if I have two of them, that's the periodic domain. You can repeat it. Makes sense? Now I think about I have two of them. This is a yellow wave. This is a red wave. I can put this two and then repeat it. Then all I did was I created a new domain. It's very easy to understand one dimension, but look at the three dimension. It's crazy. Makes sense? We get so many things. If we have time to we can make a presentation about the stuff. But this is like how much do I have? Okay, this is so making them is easy. All the just to create some kind of fundamental domain. Throw a bunch of points. Repeat them long. You get the structure. Then you can take the real You can get all of them. Like what I mean, this is really the treasure's chest. So just think about like I showed you this old uncom structure. They exist. Like think about this guys. One I showed you. They exist. Like can we come up with some kind of kinetics for that? So I wish if they do it. So you know this Einstein time. Why you know why it's called Einstein time? Because Einstein is like no, one stop. One stop. It's not included all that attention. So what we are thinking, we be able to come up with generalized version of the Einstein time. It is product it is exciting. That's what they're in that point. Anyway, you see, I'm switching down from it's very interesting because you can do the piano structure, but you can do this like piano hinge or vertex hinge because vertexes hinge are different. So there's so many things. I don't know. That's it. Because time to balance I have problem. I had any problem. That's why I had those issues.
So these are very interesting structures, and we have shown some of them as 3D printed objects.
Yeah.
Is it easy to 3D print such kind of structures? Or do you have to do a lot of work in getting this 3D printing by putting a lot of support structures? So do you recommend support structures or it's straightforward? So how do you optimize the design? Because you was talking about the design space. Okay.
Sure, it's easier.
Can you hear me? So we are using water-soluble support structures, which is easier to remove from that. Sorry, I have some. Oh, okay. Yeah.
But also in that while tuning if you use metal,
Yes.
then can because that's why working with the engineers very important. They have created a very nice building system because initially trying the our labs. There's some people they're saying, we want to work with you. We give them. Then some other papers come. Because they think mechanical property. There are so many things I can print there. Just think about this all 5 years. Yeah. They can have electronic properties. Maybe the whole structure can be integrated. So good. I'm thinking about crazy stuff because when you crack is like a resistance. When you have this thinnest, you can embed everything. Just this is the shape. Like everything has geometry. So like salt, water, whatever, everything like we can use. But also everything is very interesting. Cracks are interesting. But so, yes. Can or maybe one of you can.
Yeah, actually, I can add on that. Thank you very much. Yeah, I'm asking, what is the source of your energy, first of all? Yeah, this is my first question.
But the source of your energy.
Yeah.
What is source of your energy? It's not talking about the work.
Yeah. And what do you think?
When I put my research for cartoons, I read other interesting.
Thank you very much. Another one, what do you think about the origami? Origami.
Origami. He's talking about origami.
Yeah. You can only get that, bro. That's
okay.
I don't know if I couldn't be this is I'm talking with this is more like shape of your structure.
So you started with the chemistry as a motivation, thinking. So when finally we went into that chemistry application, it's coming from us.
I want to put physics. because it's trivial is hard problems. When I looked at mathematical paper, I found out so many interesting things. Even if you read the paper, you won't be able to understand. Either you have to talk to me like this. Crazy stuff. So exciting. I'm not talking about that this is not all mathematical. Just probably split some stuff. I suspect even the mathematicians, because they are working in the they may not see that happens. This, because this was my problem when I started. I was talking with Jonathan Cross. Cross told me, I'm talking to 2015. He was very afraid. He said that let's not use the nonsense structure because nonsense are dangerous. The nonsense can be connected. We should be able to see the nonsense. That took me, but when I see that now, that's the reason I'm saying that. If you make the headround structure, your nonsense complicated things goes to your vertices. You don't see it. It's just unavoidable. It's so complicated. Your beautiful images may not necessarily be really good. That makes sense.
Sorry, I'm going to have to go.
Yes.
Last talk. Now, people can only able to for geometry of absolute displaces. All right, thank you so much. This research is delivered at yes, which is my university on the land of Cali people in the other nation. So this is thoughts about how you can solve some practical problem on upcycling like grid shell structures. So we start from this main concern. There is some analysis that says like 40% of the global energy consumption is about construction industry. So, and basically the model is about, we build something like bespoke, right, and we destroy and build it again. So there is, I think there is a main question, which is how we can reuse components. And I think it's a very interesting geometric problem, which is not sufficiently well studied in literature, especially because it has a lot of geometric implication and considerations. So my talk is about a sub space of architectural structures, the one that you usually see in computer graphics layer and geometry processing, we talk about grid shells. So grid shells, here we have two examples of grid shell. One is at the British Museum, the other is in Abu Dhabi, it's the Yas Sultan. And basically the idea of grid shell is like this lightweight structure that allows us to cover large space. And essentially the construction is quite I wouldn't say simple because there is a lot of mechanical and statics like considerations and geometric as well, but those makes this structure very interesting from our point of view. So usually you have three kind of components: nodes, face, which usually are like made of glass, and then panel, and then sorry, and then beams, which also like support the group structure from a static point of view. So as I said, there was other paper that tried to say is like, oh, how we can actually in this context where we have these three basics elements, how we can reuse some of them in an efficient way. So this paper was presented at Eurographics last year by my colleagues from Italy, and
Well, I mean, that was kind of very interesting and a pioneering like paper on how to reuse like paints. And at the same time, these guys, they actually take care of reusing it in a way that you don't affect the overall static performance. So the actual grid shell structure is still solid, robust, and stay in place. But surprisingly, nobody have like like analyze and try to solve the problem for other kind of components. So we start saying like start attacking this problem with my PhD from a very simple perspective. At the beginning, we said, can we reuse the face panels? And this is a very geometric problem. The idea is like how you can take panels from input shape, so as much as possible, and then reuse it to actually build a target shape. So in this sense, you basically use as much glass as possible in panels. And despite this is quite simple concept, nobody had made something like that before. So, and yeah, and the solution is like requires some degrees of freedom. First of all, we want to add a bit of discrepancy, what we call discrepancy, which means like you don't want like the face to match exactly, right? The face of the target shape, even when it's absolute, you can still have a bit of tolerance, which actually is like in the real scenario, this is quite like I think it's acceptable, even because a lot of rationalization algorithm in literature of geometry of computational architecture, they actually allow a bit of tolerance between the phase. And obviously, we want to control the maximum amount of discrepancy, and we have this parameter delta. At the same time, we allow our geometry to deform a bit from the target shape, but at the same time, we want this difference to be bounded by a certain threshold, which is E in this case. So then let's say how we also, if there are other structural constraints in our problem, obviously, one structural constraint is like you cannot use a face more than once because that's a physical face. And at the same time, you cannot map two face on one source, right? I mean, one source can be used only once, and one source can map only to one face in a code because those are considered as real physical options. So, okay, so now we start saying like how we can measure the similarity between two panels. So we have a source panel, we have a target panel. So it's very simple. The idea is like we get an order of the vertices, and then you find the best reach alignment, and then you define the discrepancy of as the maximum of the distance between every pair of vertices. But I mean, I can orient the space in many different configuration because that's just a piece of glass, right? That doesn't tell me that this vertex has to be associated this way. So you can repeat this way for every possible combination and orientation of vertices. And then obviously, not only like every possible order, but because these are flat panels of glass, you can also flip. So you have several combinations, and then you try to get uh, from a source phase to a target phase, the one that minimizes the discrepancy. Right? There is only one that minimizes it, and that's the right order and the right like transformation under all these different possibilities. Okay, so now we know a bit about how a phase can match the other phase. This is quite simple, right? Very easy to implement, and it works. But at the same time, how we can find the best matching, right? This like huge space of possibilities. So what we do is like in theory we can actually substitute one face every other possible face on the target mesh. Obviously, the two faces need to have the same amount of vertices. You cannot substitute triangle with quads or hexagon with quads, stuff like that. But consider for a moment these two meshes are all made of quads. In theory, you can substitute one with every other possible in the target. So what we do is simply compute the discrepancy for all possibility. So it's quadratic, but the computation is quite fast because you just have to make a best alignment. And then obviously we don't want to consider all the possibility, but we just discard, we just use the one that whose discrepancy is below the threshold that we specified at the beginning. I mean, there is no reason to consider the one that has a higher discrepancy, the discrepancy which is bigger than the threshold set at the beginning, because those will be not good in the sense of the constraints that we specified at the beginning. Okay, so now we have to find the optimal assignments. Again, it's quite simple and it works decently, quite well. So the idea is like we just define one Boolean variable for each possible combination. Obviously, we consider only the combination whose discrepancy is below a certain threshold, not all of them, but a subset. And this Boolean variable is one if this substitution is selected, which means that the phase I on the source is used to substitute the phase J. Okay, at the same time, what we want to minimize is total discrepancy. I want to have to find the best association as possible between phases which are similar up to rotation, translation, and flip, and possible combination. But if you try to minimize this one, obviously you will select nothing, right? Because it will say like, okay, the minimum is like all bi are at 0. So we have to add another 10 anchored to like invite the solver or to push the solver towards selecting some of them. And we have this lambda parameter, which actually the meaning is like, and it's another parameter that the user has to select and tune a bit. But the idea is like when you have a high lambda, you have a low discrepancy. The low lambda, you have a high number of substitution, right? And the mid higher discrepancy. So this like counts how many substitution you allow versus the overall discrepancy. Okay, finally, as you remember at the beginning, I said we can only use one substitution. We can only substitute or use one phase only once, right? We cannot use the same phase twice. I mean, it's a physical option. So which means that for each phase, the rows of all possible assignments, there is only one assignment. And this boils down to a simple constraints again to this IMP. Okay, so once we have selected the amount of the possible like substitution, then we actually use we take the source phase, right? We get the best rotation and translation given the substitution that we obtained with our IMP, and then we proceed, right, one by one, starting in a greedy sense from the one that has the lower discrepancy. And then we assign it, and basically we do an Arab deformation on the surrounding to actually massage the mesh to adapt to this substitution. And if you remember, we have also a threshold on the maximum distance. So which means that if during this massage the mesh goes like the distance to the target surface exceeds a certain threshold, then we reject this substitution. And at the same time, like you may notice that multiple phase can share a vertex, right? So this position is going to be average every time we put a new phase. And in case, again, the new substitution violates some of the constraints, we reject that substitution. So then we embed this cycle of ILP plus substitution in a bigger cycle of optimization, because why do you actually do this substitution? Basically, the mesh deform a bit, and also not only in 3D, but also in tangent space. So all the tessellation adapt. And in theory, right, you start with a set of substitution, then you, by solving your IFP, then you deform your mesh by using your ARA with a source panels with target mesh, and you get initial substitution, but you can actually continue. Start again from the beginning, from the target chain, and substitute another set of faces. Right, and here there are several possibilities. You can keep the one that you have at the beginning. You can start from scratch, or you can select several percentage. Right, we have some analysis of this behavior in the paper. I mean, the behavior is quite stable, doesn't change a lot, but there are different strategies how you can actually implement this kind of substitution strategy. Okay, so the main parameters, I say we have several parameters, the max, error, and the lambda, but I think one of the important that deserves to make a separate ablation study is the discrepancy. Obviously, the smaller the discrepancy threshold, the less the substitution you allow. So in this case, you see that blue faces are the one reused from the source, and red are the one mapped. And in this case, the mask discrepancy is measured as a percentage of the average edge length. It works quite surprisingly well with triangle mesh, especially the regular one, which are the ones that are usually employed in the architectural case. So these are meshes in order to actually dimension in the real, like to have some dimension that match a real world scenario. We thought about these meshes to have an edge length of around 80 centimeters. So these panels are triangle, like with 80 centimeters length on each side. And then the results are pretty good. You can actually reuse 92% of the phase from the source, 83% mapped on the target, and you can see that the distortion discrepancy, here it's called distortion, sorry, but the discrepancy is like in the order of below 1 centimeter. So if the panel are 8 centimeter, and most of them are 0.2 centimeters. So I think it's quite good in terms of and useful in the real scenario. And here you can see also the distance. Most of them they are like below 0.1 centimeter. So for triangle mesh, it works surprisingly well. Here there is some other example. And you can actually see this example in the paper if you want to have more details about the statistics. Things get a bit more complicated, but still work decently for quadrilateral mesh. So in this case, we have two meshes with, obviously, with quad mesh, you have more combination. It's so difficult to match the shape of a quad, and it becomes incrementally more difficult. I mean, if you increase the number of vertices. In this case, the average length is half a meter, and we reuse a lot, but at the same time, distortion, I think sometimes is 5 centimeter, which is a lot. If you think in practical sense, obviously you can have some practical solution, right? Or you can decide to discard some of them if you want, right? And put the threshold a bit lower. Yeah, these are other results for mesh, which confirms with the trend that yeah, you can see that for some meshes with distorted quad, it's difficult to find the elements with the same distortion. And indeed, here we have some lower ratio of reuse. We also tested with generic mesh, so here it's mostly hexagonal mesh, but you can see there are also pentagon, and I think it's called heptagon, with 7. And yeah, even in this case, you can see that the amount of distortion is quite high in this case, but still, I think it's, if you think the average edge is 91 centimeter, you have 3 centimeter of threshold. Obviously, that doesn't match precisely, but you can actually figure out ways the practical sense for lower down the threshold. We also tried with the real world scenarios. So we took the real world mesh of the British Museum, and that's the other Lilium Towers and other real world British chat that you can find online, and tested what is the usage, how much you can, in theory, use this one to actually rebuild one structure starting from the other. So obviously, right, the reviewer asked us to make this nice study, which I think it's important how much is the past. And because in architectural geometry, most of the mesh are regular, they have nice tessellation. But what happens if you take a mesh and if you basically decimate with quad, quadric collapse, so you have a lot of different shape of triangles. So obviously it works in terms of that it doesn't crash, but you cannot expect to have the same performance. And here we see that the reuse is quite lower, and the distortion, we had to add a bit of higher distortion in this case, even though it's one more than 1 meter and the distortion is like 2. So to conclude, I just think that it's an interesting research direction to use computer graphics and geometry in general for upcycling. Like there was in the last year, there is a trend of papers like trying to do upcycling in garment design or in real object trying to reuse parts of the surface to match other surface. For example, other paper presented like a couple of years ago, 1 year at SGP was very interesting. But in the case of architectural geometry, I think it's this one and the other paper that works with beams are somehow the first one. And there is a lot of space for research. For example, one can, okay, I mean, we saw that the problem of beams, the problems of like faces, but why if you combine them together in the same, in a unique optimization framework, that would be interesting because they are like interconnected. And I think another direction would be like include FEM analysis while optimizing because you, I mean, basically when you change the geometry and tessellation and the position of nodes and beams, you actually change the static properties. And as well as try to formulate this problem in the continuous setting. So I don't have a target meshing, I just have the target shape and the source meshing, right? How I can solve this in the continuous setting. So this is just the first step. I think it's interesting. I hope you enjoy the talk. And yeah.
You said that once you select a phase, you are not going to select it again. So that basically, is it brought to the starting phase? The entire method. To answer the question a little bit, if you start from a different phase, then the mapping might have already been done. So how do you know that you are starting from a reasonably good starting point?
No, we have no, I think we don't have a starting phase. Basically, we have a set of candidates. We have a set of candidates which are all possible pairing, right? And we filter out a set of candidates, and then we solve an ILP, right? This ILP tell you what are the substitution that you have to do. Then obviously there is a step which is order dependent, right? But the substitution, you already have the substitution. Then you start, we can actually do these one by one assignments to control also how much it deviates from the final shape, right? And yes, you're right. I mean, if you start from a different shape by applying this deformation, you can actually converge to different ones. But we start with the one that has lower discrepancy, so then generate less deformation in the mesh, we keep adding, right, one by one. Because it's difficult at the same time how to apply them, right, and which order to apply. So we find the best candidate, which are consistent from a topological point of view, we start adding one by one.
So it's always unique. In that case, we could still have more solutions for this.
Yeah, we can have different solution if you start from different ways, but the assignment is unique.
Yeah, yes, thank you for this wonderful talk. So maybe I missed something. So you have an input phase and you have an output phase. Input shape and output shape. And I was wondering what is the logic between having an input shape? Because I think if I have a company running all these architectural shapes, I think I have a bunch of triangles and I do not have a single input shape. So maybe there's something I missed.
No, the idea is like to upcycle an existing object, so it's already there. So it's the idea is like we want to. I mean, we have an object which is already there. We want to upcycle components to construct a new object instead of like demolish. Maybe I haven't explained too much.
That's fine, but I was imagine you are such a company that building some stuff. So, okay, you are building one input shapes. Maybe during this build you have made some mistakes, so you have a bunch of triangles that maybe are valuable for builds. This is why starting from only a single shape.
Yeah, I mean you can start from multiple ones. I mean it's like or I mean
but maybe it doesn't change how to build up.
Yeah. Yeah. I mean that's the idea is like to start something that exists already, right? And you somehow want to demolish but reuse it. So there are a lot of other possibilities. For example, I mean, following your intuition, one can design instead of like you can design a set of modular pieces that can be used for multiple shapes, right? And then you can write the best vocabulary that allows you to do a lot of different shapes and similar to a transition problem, but extended to multiple shapes. Yeah.
Thanks.
There's a question there. Sorry.
Start with so I love the concept of trying to mix and match this force without touching the transport. It's very cool. But it's so that the buildings want to recycle as that I thought they would not really this.
I don't know if they did this. I mean, it's a good question. It's yeah, there is some energy involved in actually like this like disassembling some structure and using it in another way. But
and they do recycle the glass because it's much cheaper in terms of CO2 emission and stuff to recycle the glass rather than starting from the raw material. The shape,
yeah.
Not from the same shape.
Yeah, I mean, that's an interesting question. I mean, we can, I mean, for the moment, we recycle the glass, but we are working on the future direction in recycling also the beams and the nodes as well. Which is, which is also like steel, right? Which is maybe more profitable in terms of circular economy. But if it's good for construction industry, I don't know. If yeah, maybe it's good for like telling the story and getting grants.
So we are a little bit late. We are behind the schedule. So we will directly go for a Spm and a Smi. So if you when we start with them, then it will have time to get up from us. Even we use that right now.
actually moderate this SPM and SMI award ceremony. So we are a little bit behind the time schedule. So guys, I have to wait. Let's do it. So the agenda for today, I will briefly introduce SMA Association, and then we dive into this SPM and SMI awards. I will present the SPM awards, and then Erwin will take over with SMI part. So a few words about Solid Modeling Association. So actually, it is the community. It's us. Yeah, it is people who kind of deal with CAD topics and problems that go around solid and physical modeling. We have this web page, solidmodeling.org. And if you are not member of the community, you can join it rather simply by clicking on this link and register. So this SMA association is kind of led by so-called executive committee. It is 5 of us: Ligandrio, Konrad Turkiye, Shell, and Shinli, and myself. Actually, Konrad and Shell are here. And you see that our terms finish this year. So this is why it's in red. So I would like to encourage all of you who are willing to do the surveys, please, one of us.
Better. Okay. Yeah. And actually, the responsibilities are kind of taking care of the organization of SPM, say assign organizers, and take care of the awards and SMA webpage. So above us is so-called advisory board. So I'm showing also the senior members of the community. Unfortunately, none of them is here with us today, but the advisory board members are Gershon Elber, Jarek Rosignac, Vadim Shapiro, Wemping Wang, Jessica Zhang, and Jan Warderbrande. Wemping has decided that his term will not be extended, but the other 5 has agreed, and they will keep serving as advisory board in the coming 2 years. So that's the SMA kind of committee, and let us move on. So one of the main objective of the SMA is this SPM conference. So this is where we are now. And this SPM conference is linked to the special issue of CAD Journal. So you have seen the statistic presented by Xiao on the very first day. This year we had 13 accepted papers, I guess out of 54 submissions. So I guess this is very nice, around 25 acceptance rate, which is really great. Plus there are another 9 papers that got referral to CAD and that are being hopefully accepted in the coming months. So that's it. Yeah, and I would like to highlight, yeah, that this conference has a long-standing tradition with CAD Journal, and we will continue with that. So the SPM awards. Let us move to the main course now of my presentation. So let me introduce briefly the 4 categories that we have. Yeah, so the most kind of prestigious and most senior is so-called Bezier Award. This has been established in 2007, and this is a long life achievement award. The second category is Pioneer Award. This has been established in 2015, and the awardee gets the reward for more than 25 years contribution to the field and for significant impact to the field. And then we have 2 more categories. Fellow Award that has been established in 2019, which is for also distinguished researcher who also demonstrated support to the SMA community and also has outstanding research record. And finally, we have this Young Investigator Award that in the past has been called Young Investigator Award, but we have a change since this year. The award is going to be named Cohen-Wiesenfeld Young Investigator Award. And the reason for that, yeah, maybe many of you know, sadly, Elaine Cohen passed away last year, and we have decided to
commemorate her achievement and name the young investigator after her. Yeah. However, Elaine Cohen and Richard Riesenfeld were kind of inseparable, both in personal life and also research-wise. So we have decided that the award will carry the name of both of them. So since this year, it is Cohen Riesenfeld Young Investigator Award. And this award is going to be given to outstanding young researchers in terms of assistant, respectively associate professor level, not PhD students. But yeah, so the candidates should be younger than 40 years of age. We have this example that for this year, yeah, the candidate must not have his or her birthday, 40th birthday before January 1st, 2026. And last but not least, I would like to also announce a very nice kind of achievement. And this is that Maxwell Henrehen Foundation stepped in and decided to fund this award by very generous contribution. So this foundation that supports also other researchers and activities gave a donation to SMA, and it will be set up an endowment, and the awardee will get approximately 2,500 US dollars, depending on the country of residence and depending on taxing. But I believe this is something very nice, and hopefully in the coming years, yeah, we will have the awardee to come personally to SPM. So this is Cohen Riesenfeld Young Investigator Award. And so let me move on now to the award ceremony itself. Yeah, so we have 4 awards. I will also briefly say a few words about the Bezier Award. So this is the most prestigious award that is named after Pierre Bezier, who was an engineer in Renault. Many of you maybe know his work, and I would really like to say that it is really amazing that kind of a small yet beautiful idea can change area. So actually, the SMA Association named the award after him because his kind of achievement really demonstrates that one kind of nice observation, that change of basis can really make life a lot simpler. And in honor of Pierre Bezier, so this award has been established in 2007. And since then, we have many awardees. Yeah, so I'm just showing for the sake of time images. Yeah, I will not name all of them, but you can go to the solid modeling homepage and you may see very many famous and outstanding people. On these slides, sadly, Elaine Cohen and Malcolm are not among us anymore. And from the more recent awardees, we can see another batch of outstanding researchers. And I'm showing this especially for the young members of the community. So maybe you have read books or papers of people whom you did not know the faces. So go to the SMA homepage and you may kind of match the faces with the work they did. And luckily there are still many of them alive, and some of them even among us today. Yeah, so let us move to the Bezier Award winner. So before I will reveal the secret, I would like to share some statements, and actually these are the statements of the nominators, and these are the statements of the Bezier Award jury, how they justified why this person has been given this award. Yeah, so I will not say the name, but I'm saying the Bezier awardee was one of the early pioneers who investigated the integration of BREP, solid modeling, and parametric surfacing techniques. Or the Bezier awardee is widely credited with reverse engineering as a separate research discipline. He or she, together with Ralph Martin, established the standard pipeline used by nearly every common software today, starting from data capture over mesh processing, up to segmentation and surface fitting until the BREP model construction. So, and last but not least, the Bezier awardee also developed various multi-sided surfacing schemes, including transfinite and generalized Bezier patches. So with all that said, I hope that you already are guessing that the Bezier awardee of this year is Tamas Varade. Tamas, please. Congratulations.
Thank you very much indeed.
Now, clearly, such an award it's not only it means that there are lots of people really who are in co-creation. When I will see what all the organizations and scientists are actually giving all of money. Then, thank you. Then I joined a US company called Geomagic, and I was responsible for their product line, flagship product, Geomagic Studio. And then in 2011, I returned to academia and I work at the Technical University of Technology and Economics, where I am professor emeritus. Well, actually, in 1976, that was exciting. I joined the institute, and then I met two fantastic persons. The first one was Steve Koons. He worked at the institute, so he was the first inspiration. The second was Malcolm Sabin. He worked on his PhD, and it was very, very influential to me. So Malcolm, I will not be here unfortunately on Thursday. So let me tell you that Malcolm was a good friend, a good mentor, a good colleague. And actually, I can show you his PhD with me, and I can show you handwritten notes by Malcolm Sabin. So if someone is interested, it will be with Peter Salvi, so you can look at this. Then there were three important university visits in my career: Cambridge University, Arizona State University, and Purdue. Now, I would like to express my gratitude to my co-authors. There are many brilliant co-authors around me, more than 25. And maybe there are four names I would like to highlight. Ralph Martin, Alan Rockwood, Peter Salve, and Martin Waitkus. Three of us still form a little geometric modeling group at the Technical University. So thanks to everybody. Now let me do a little commercial to my presentation tomorrow. It will be about reverse engineering, various topics, pipeline, triangulation, segmentation, surface fitting with labeling, blend reconstruction, constant fitting, so various aspects. You can see that the yellow topics will be touched tomorrow. And another major block, multi-sided surfacing, again started with overlap patching, setback vertex blending, multi-sided Kunz patches, transfinite interpolation. And then we started to deal with the generalized Bezier patches. And tomorrow you will hear about three different schemes that are generalization of the quadrilateral Bezier. So this is it, and thank you very much indeed. Thank you.
Thank you very much, Tamas, and big congratulations again. So we are now moving further to the next category, and for that we have our awardee who is online. And yeah, so the SMA Pioneer 2026 is Binding Guo. Binding, do you hear us? Excellent. So big congratulations, Binding. And we are sharing the presentation now. We are sharing the presentation, but I will have to drive. Yeah. So you will tell me when I need to move on with your slides. So please, the stage is yours, but use me as a puppet to move your slide further.
Okay, thank you, Mike. All you can see. Thank really appreciate my nominators, the commission for selecting me. And also, I'm very honored and very grateful to my co-author, especially my research team at the Microsoft Research Asia. So today I'm going to talk a few pieces of work and then highlight some strengths have emerged for my career. So the first slide two. Good slide.
Okay, then we need to share it with you. Okay, do you see? Okay.
Yeah. So one thing I really enjoyed working out with my esteemed colleague Jay Manor is that that town. So every time we go on by today with the transformer and then here you can see the main plots. Not to get the circle that where we have to controlling the we move it around understanding the shape of the surface. Well, this is done with the usual beginner task. Of course, we're doing the use cases form, and this kind of revised form. So, so one of the fundamental challenges here is that, first of all, what are the values of the point position? Because many of the point position is not valid. And also, once you have identified the valid control point, if user wants you to move the control point to some point, you want to choose the point that's closest to the user topic. That's still valid. So it turns out that there's a very deep fundamental problem in there. To use a cone factor condition, going to decide the value control point. In fact, we can use a linear form of compactor condition to verify that the control point itself doesn't exist. And then we use this distance, which is actually the non-linear compactor condition to choose the control point that moves closest to the user copy. So the fact that I learned from this project, so is that it gave me a chance to appreciate how compact, how simple, how beautiful Brazilian paths is. The Brazilian surface are probably the most beautiful thing that I've ever worked on. So that's a deep impression on it. Next, please. For the next piece I'm going to talk about is someone who has started to mass testing with my esteemed colleagues, control, Vito, and my Microsoft research team. So this is a new way doing mass testing.
This diagram, when everything explicitly, everything that mesh vertices, this new approach asks everything the vertex gradient, another position. This is counterintuitive, but it has a very fundamental principle behind it. It is based on the fundamental law, which here I just gave it an informal called the Poisson plan. So what does this Poisson plan do? Let's start with the lower left quarter of the triangle. Suppose you have a stable thing. In this case, we are using statistics, like electrostatic as an example. So because this is a fundamental the operation of the whole work in Newtonian. So if you start potential and fly, and you take the gradient, then you get a vector. That vector actually is the not the gravity, that is the actual static. And if you take a magnetic whole, that magnetic vector, and then you end up with with the density. So, of course, so the rule semantic says is that the field after taking a classic operator should be after taking the classic operator should be equal to the density. So this is a fundamental law dominant electrostatics science in the field. The same triangle works for you just have to say to yourself, then what's more amazing? If you could use a mixing that process static mentally, ideally it is, and do the same thing, then you would achieve quantum inequality. And what we have done with my colleagues is that we realize they have continued to play further with geometry. If you take a lens and see the potential field and go through the same quantum track, then you will end up with the quantum velocity, which is much more quite like a method in tool existed at that time, 2002. 2002. And so what as far as I have learned from this is that when we work with mesh, it's more like logic. It's not compact, beautiful, like reduced still we can use fundamental nature, fundamental one useful mathematics, and mathematics to control the something. So that thing is how good. This work much more interesting. Yes, it is. Just, just, talking about sleeping is a transformer for 3D understanding. So now we're working with point cloud. We want to understand this point cloud, understand with the going to share, table, and a lot of stuff. And so the key idea is swing. Swing means shifted window. The shifted window consists of two concepts. One is shifted, one is window. So window is a new equation mechanism. As you can see, the window is represented by the red square. So unlike vanilla heat transformer where you compute an interaction between every pair of the three packets. This method can allow you to constrain your computing interaction only within the window. Then, of course, you can see that it goes up because there we want instruction to the far away type packet. And how that is mitigated because this is a hierarchical transformer. So we do the on the next level, then later, uh, we shift the window. So that's where the shifted comes from. The shifted window, because now the window they have no overlap. So the information from one window will pass on to the next. So this setup is very efficient and effective. The window of intention reduces computation from n squared. And so this is um, one part. We are working with new features. This is really very close to more than and but we can see that fundamental principle. And here in fundamental principle is the induction bias is a file, local file. The client, this file means that um, they don't find point. Their interaction are more important than interaction from far away. So here, just now, point out that when we work with geometry, we always end up with very stuff that's very much important. And then the people in the general machine learning domain start. Why do we have to practice weighing numbers? So why can't we just use the validation transformer? Because the data processing, the point is just data. They should not specify the point because in terms of the background, we do have the data and unit data, they are special. They cannot be handled by um, general purpose. They are not like they
Okay,
cannot
binding.
using transformer.
We are running slightly out of time, so please let me let me cut your short pitch and let us sorry for that, but let me yes, so thank you very much, Binding. Yeah, thank you, big applause for Binding. Yeah, okay, thank you, Binding. Okay, yeah, but very shortly, please.
Geometry impact basically geometry is often so fast, but visible. The deep geometry moves. The not too fast, but real fast. So we have the force of thank you. Thank you, man.
Thank you, Binding. Thank you very much, and congratulations once again. Okay, so we can move now to the next category, which is SMA Fellow. And for that, we have our awardee here. So let me reveal the secret. And the SMA 2026 Fellow is David Xianfeng Gu. So David, please come on the stage. Deliver your pitch.
Sure. Thanks. Yeah, it's my great honor to receive this kind of prestigious award. I would like to thank all the committee members and all the organizers. Okay. So basically, my research focused on developing a interdisciplinary field called computational conformal geometry, which combined modern geometry with the computer science and applied for a neural field. So basically, we have systematically developed theories and a computational method. For example, we developed harmonic maps among surfaces and from manifold to graphs, so which leads to computational method for foliations. Then by collaborating with a lot of people, we developed this field called decomposition, like Professor uh, uh, mm, okay, matrix here. Yeah. Then this basically generalized finite element method to exterior calculus. Then later we developed discrete surface receive flow. We know receive flow was invented by Hamilton for the purpose of proof concurrent conjecture, and Perelman used that to really prove it. So this is the only method so far which can construct manometric from curvature. Conventional finite element cannot do such kind of task. And recently, we developed discrete Riemann-Roch theory. So basically, we know given the surface, the chord meshes are infinite, but the dimension is finite. How can you calculate the dimension, which depends on Riemann-Roch? So here we show one picture. Actually, this is very fundamental theorem in surface differential geometry called uniformization. So which claims that all the surfaces can be conformally deformed to one of three canonical shapes, either sphere or Euclidean plane or hyperbolic plane. Yeah, so this theorem was proven in 1910. Then after 100 years, we reprove it using discrete theory. And so for the spherical case, we use harmonic map. For the computed here, this is the composition. Computed here, using a receive flow. So then, so we see it took 100 years for people to develop from theory to computational method. And the same picture holds for three manifold. There will be 8 canonical geometry, and I don't know how many years that will take. For young generation here, that could be a good direction. And recently, we are using geometry to do AI, which is called geometric version of approach for optimal transport. So we know that for AI, everything is a probability distribution. So the fundamental task is how can we calculate the transport map from one distribution to another distribution. So this reduced to something called a Montagne equation. So we have developed a computation method for Euclidean spherical and hyperbolic background geometry to compute these OT maps. Then so here we see that Montagne has a very profound geometric background. So basically here is that if Gaussian curvature is found on a planet domain, how can we find convex shape with prescribed Gaussian curvature? But then this is called Snell theorem, and we give a new proof for this theorem, and this new proof leading to the computation method. Then from this method, we discovered that there's an intrinsic fundamental flaw for modern AI because this mapping is discontinuous. But if you are amenable to only that units map, okay? So then if you see the same law, no matter how continuous values, how many figures you're building, so because the money is therefore for API, if you're a model, you're writing, so then none of them can imagine use. So basically, from geometric perspective, we can improve the current generative AI. So then we apply these theories for solid modeling and physical modeling. So basically, in the early work, we try to answer the question why we cannot construct slices on surfaces. Then we guess that all slices conform depends on how geometry. And in general, there's lots. But by removing
we can using this rule. So that is the right foundation for medical science. And then later, by other readings of these, we have become one nurse or IT nurses, which leads to how I track all medical space. So the fundamental function of track concepts are there in the having which of similarities of knowledge. Now, for example, everybody knows component versus the knowledge. It's equal square. 1 degree 3 square. But there are some free field with equal square. What's the reason for that? Usually, using something from grammar or only without a break. Geometric or family equation square, which is our fundamental equation. And this is a theory. Wow. Function of G groups. Originally, we compile a set of compact fluid from human and one for each slash. So alongside all of my advisors, mentors, collaborators, and the students, Professor Chen Liao, who led me to the field of Professor Remember, who led me to the field of computation, professors speak orally to the field of computer graphics, event processing, young leaders, counselor, companies, company, and intelligent, and current professor planning, Dr. Hans, Jessica Lam, 徐雪瑶, 李刚刘, Yin He, 小火锅, and Xin Li, and all many others. Okay, thank you very much.
Thank you very much. So we are moving to our final category. So let's not steal the thunder. Yeah. So our Cohen Riesenfeld Young Investigator 2026 is Justin Salom now. Justin, do you see us? Do you see the slides? Okay, just a second. We should also see you. And you should see the slides. Hopefully now. So just the stage is yours, and I'm controlling the slides.
So, we said much more instruction. Yeah, probably the logistics completion of the program that I'm running. So, very good. Right, so we just a tiny bit about our research, and then of course, thanks to many people that really know this work to. Essentially, our team's work studies what I've come to kind of call geometric data processing. So basically, I follow my own path of research, which kind of goes back and forth in low-dimensional geometry processing, 3D, and so on, and high-dimensional aspect of machine learning related. So specifically, for example, many years ago, with friends at Stanford, we were able to work on algorithms for computational transport, and that was just emerging that some application would lead to the dimensions. And then eventually we realized, what previously, many of the applications were relevant not only to that particular domain, also to high-dimensional inference problems. So we developed some of the early architectures, for example, for doing machine learning with optimal transport kind of built in. And use it as inspiration to study other problems of the intersection of geometry and data, where maybe a data set has a problem as a high dimensional, has some geometric structure we can leverage. So that really reflects the kind of work that we do in our team today. We have about 50% of our students are working on low dimensional problems in computer CAD, design, computer vision, and so on, including some physical solutions. And the other half of our work and kind of running and by having some
mutual collaboration and understanding, we can benefit both sides of this research agenda. If you don't mind going to the next slide.
Yeah.
So first, it's such an honor to receive this award. I wish I could do so in person and to thank everybody that's there. But I really should acknowledge that it was only possible due to this fantastic ecosystem and set of members and advisors and collaborators who are really the folks that are. I just have been so lucky to be the privilege to really join people who work with throughout my career. Of course, I really should thank you, Kivas and Nathan Busher, who sort of co-advised my PhD and got us started on this path, as well as many of the mentors who I've had the pleasure of working with throughout my career, all the way from Stanford to Pixar, Princeton to MIT here, and a lot of other stuff along the way. Can you go to the next slide, please? And these days, our research really is supported by this fantastic team, PhD students, postdocs, and so on. You have the MIT Gene Data Processing Group, and really everybody in the room today is encouraged to come to us in Boston and tell us all of the geometry problems that you're excited about. You go to the next slide, please. And in particular, here I tried to be completionist about them, to think all of the members of our team over the year, but I'm just seeing, unfortunately, it's from like we've been here at MIT for about 12 years, and already fantastic characters across levels from postdoc to PhD students to masters and undergrad interns, all of whom contributed to the research enterprise that we have. I'll find one more slide if you don't mind. Fantastic set of collaborators that we have, not just across the world, including probably many people that are in the room today. I tried to compile a complete list and just stick it on the slide. I wish I could acknowledge all of the really people on this list and the remote from home. So anyway, thank you all so much for this award, this honor, both to speak to you today. We really appreciate it, and really the geometry research community on the Black side is such a fantastic place to be, and a really interesting and collaborative event. So I hope everybody gets a chance to reach out and visit us at MIT to collaborate around here, and I look forward to seeing everybody soon. So thank you very much.
Excellent. Thank you. Just congratulations, once again.
Just close it.
Okay, yes. So to conclude our ceremony, I would like to say big thank you also to the people who selected the awardees, because without them, our job would be kind of impossible. Yeah, so you can see the names of all four SMA juries. Yeah, you can see that some names appeared in more categories. So I would like to thank to those people even more. They had a decent workload with all the meetings and with evaluating our candidates. So I would also like to ask you for a big applause for our Senate juries. So with that, I'm concluding my part. I would just say that the SPM Best Paper Award is going to be presented at the very end of the conference, as usually, and we will also advertise the event for the next year. And this is going to be done tomorrow or also during the very final ceremony. So now I would like to ask Ergun Ackelman to come here and continue with the SMI part. So.
Yes, yes.
Go to web. So actually our talks are Friday. So we don't have any talks. And then I will just tell you briefly about our works. If you go to the SMI page, and from the SMI page, you can go to the SMI main page. In the SMI main page, we have the explanation of 3 different awards. The first, since we are waiting, and then I don't want to spend too much time because we need to leave. Okay. Just yes. Exactly. Can you go down? And then I can talk. But we don't see it.
Sure.
Okay. We have 3 awards, very similar to SMA awards. And then our best award is called the Kuni Award instead of Bezi Award. And then this year, 2 people won the award. And then Yarek will give the talk, and then Malcolm Sabin. Yarek was also the Bezier award winner. And then he will come and then talk to us through Zoom. And then we lost Malcolm Sabin, and then we will have a commemorative session for him. People will come and then they will tell like how they remember him, etc. Like also, any of you want to say anything about him, you are welcome. We will try to keep exactly the 20 minutes, but is Brian here? Brian Weibel will run the session, and then yeah. Yes. Okay. Then current award committee is like the Bianca Parsigliano is the chair. She is not here. Therefore, I'm talking. Myself, Stephanie, and Jörg are here. And then you can also talk to them. The important thing, we want nominations. Okay. Like the one is the, as I said, that Kuni Award. The another one is the Young Researcher Award, and another one is the Service Award. Service Award is generally internal, like because we know who is doing what, blah, blah, blah, something like that. But if you have a PhD student who finish doing very well, nominate them, okay? Because we cannot know, like we need your nomination. Also, the same goes with the Kuni Award. For instance, we made a mistake, clearly. We were late to award Malcolm Sabin. We lost him. We gave the award, just a month later, we lost him. So another important thing, we should be able to recognize people like when they are with us. So you can see them. So there will be talks, and then over there I can talk. Like we don't want to spend too much time because we want to leave. Okay, thanks a lot.